everyone. I see that we've got 39 participants already. Welcome to the AAVSO Spectroscopy workshop.
There is a chat icon in the bottom of your Zoom screen, and you're welcome to click it and chat with other participants. Just let us know you're here, where you're from. That way, while we wait for everyone to join the webinar, everyone also has a chance to say hi to one another.
One of the things that's exciting to me participating in this workshop is that we have participants from so many different countries. I haven't had a chance today to count up the countries, but I know that it's more than 20. And we have people participating from all over the world today. So I think that's a very exciting thing. And it's one of the fun things about spectroscopy and amateur spectroscopy is that we do have a very international community. And it's just wonderful to see everybody participating and making new friends and learning about spectroscopy together.
We have most people here. I think we're waiting for a few more, so we'll just wait another moment just to give everyone a chance to enter the webinar.
If some of you are wondering where some of the panelists are from, Stella Kafka is in the Boston area, and Lindsay is also in the Boston area. Francois is near Grenoble in France. I'm in southern New Mexico in the United States. Tom Field, who's here, is in the Seattle area in the United States. So welcome to all of you. Oh, I see somebody is here from Whidbey Island outside of Seattle. Well, that's a beautiful area. I've been there before, really loved it. There's a lot of places here that I've been that I really enjoyed.
It's really wonderful, as you mentioned, Ken, to see where people are coming from. We have individuals from Germany, Turkey, Myanmar, Canada, the UK, Rhode Island, our neighboring state here. Hello, Arizona. Good morning.
Yeah, Italy,
Winnipeg,
India, England,
France, Australia. What time is in Australia? So wonderful to see you. Oregon, New Jersey. Hello, Texas. It makes you feel that you are part of this community. It's such an intimate experience. I mean, we're social distancing, but we're not isolated. So it's so wonderful. I love this.
Hello
India,
to Queens,
hello, India.
New York.
Beg your pardon?
I said hello to Queens, New York.
Yes, hello to Queens, New York. Hello, Spain.
Yes,
hi,
hello.
Barbara. She's
hello,
in Florida.
India. I've been to India
Oh
before.
my gosh, Australia, it's 3 a.m. apparently, Euro says.
I hope you're observing. Oh.
All right, I think
no.
so.
Okay.
We don't get too far behind on time. We're going to get started. Looks like a lot of people are in. So welcome everyone. I'm really excited for this day 2 of Ken and Francois' spectroscopy workshop. And I'm heard such great things about the first day last weekend. And so I'm really excited to hear from all our presenters that we have today. Just so many presenters talking about so many different topics. You can see here on the schedule, our schedule of events today. I would also really like to thank our sponsors, OBSTech, Optical Structures, First Light Observatory Systems, QHY CCD. They are all really instrumental in helping us as a nonprofit be able to do what we do for everybody. So thank you to them. So here you'll see that we have a Q&A button set up at the very bottom of your screen. You can click that button and you can type in a question and it will be read by Ken, and then whoever is presenting will verbally answer that question. We will be disabling chat while presenters are presenting. You wouldn't be chatting with your neighbor in a in-person event while there's a presentation going on. So we're trying to follow those same practices in our online event, just to make sure that there's no additional online noise and distractions going on. So with that, I give you Ken Hudson.
Hello, everyone. I wish I could say it's great to see you. It's a little disconcerting with webinars to not be able to see the participants in a meeting, but I know you're all out there, and it's good to meet you virtually, and welcome to day 2 of our astronomy workshop. Last Saturday with the introduction to spectroscopy, I thought went very well. We had a lot of really good questions, and I'm looking forward to all of today's presenters. We have some really good people. Before we get started though, I just wanted to say a few thank yous. Same people that I thanked last weekend, but thanks are definitely in order to the AAVSO. Without the AAVSO, this workshop would not be happening. And it's a great organization. I would recommend that you take a look at aavso.org, the website, and also look at the AAVSO on Twitter and Facebook, and consider being involved with the AAVSO in the future. Specifically, I'd also like to thank Stella Kafka and Gordon Myers. Stella is the executive director of the AAVSO, and Gordon is the president of the board of the AAVSO. Both of them have been extremely supportive and helpful throughout this whole process. I'd like to say thank you to the AAVSO staff. Every one of them has worked really, really hard. And in particular, I'd like to say thank you to Lindsay Ward, who has just done an amazing job. And so thank you very much to Lindsay. Thank you also to the Scientific Organizing Committee. They're the people who came up with the speakers and the presentations for this workshop. And the SOC was comprised of Francois Cochard, David Doctor, Woody Sims, David Whalen, and Stella Kafka. Again, a tremendous amount of work, so thank you to all of them. And then finally, thank you to Joe Daglin, who helped me organize the first 2 spectroscopy workshops that were done here in southern New Mexico back in 2018 and 2019. And if we hadn't done those, we wouldn't be having this now. So thank you very much to Joe. Before we get started, I just wanted to remind everyone that our theme last weekend was it's all about the science and the fun. And that still holds true today. It is all about the science and the fun. And so hopefully you'll enjoy this session. Lindsay already showed you how to ask questions. It's the same way we did it last week. We'll be holding the questions until the end of Coralie's presentation, unless there's something that needs to be answered urgently, but I'll keep an eye on the questions and answers as we go through her presentation. And then finally, all of the presentations are being recorded and will be available later on. So you'll be able to watch them again if you choose. So with that, I'd like to introduce Coralie Neiner. Coralie is an astronomer at the Paris Observatory at the Meudon location, which by the way is beautiful. It's gorgeous. I went to a meeting there a few years ago with Coralie, and it was one of the best things that I've ever done. It was so much fun and so interesting. Coralie was instrumental in the creation of the BEST program, BE Star Spectra, and the BEST database, and along with a lot of very, very active amateurs. And between them, they've created one of the best professional amateur collaborations in all of astronomy, and probably one of the best professional amateur collaborations in citizen science. So with that, I would like to introduce Coralie.
Thank you very much, Ken. I will share my screen. I hope you can see my slide fine. Yes? All right, then first of all, I would like to thank Ken and Francois for inviting me for this keynote talk to speak about these pro-amateur collaborations on BE stars. And also, of course, thank all the organizers of this great meeting. I hope to be able to be with you later today and maybe tomorrow, but I cannot guarantee it. So if you have questions about my talk, please ask them preferably right after my talk in case I cannot come back, but I will try. All right, so since I'm going to talk about pro-amateur collaboration on BE stars, I guess I should first talk about BE star and let you know what they are. So what we call classical BE stars are non-supergiant hot stars that show emission line in their spectra. And this corresponds to about 20% of all B stars in the sky. So they are quite numerous, several, well, about 2,000 BE stars that we know. These BE stars have a hot polar wind, but more importantly, they have a cool circumstellar disk. And this disk is not an accretion disk like we see during stellar formation, where matter falls onto the star to create the star. It's just the opposite. Here it is a decretion disk. So it is matter that is ejected from the star and that forms a disk. And so this is very special among hot stars. These BE stars all rotate really fast, on average 250 kilometers per second. And because of that, we will see later that they are not spherical, they are flattened. They are not really spherical stars. And we also know now that basically all BE stars pulsate. That means that there are oscillations in the star and they are deformed during the time. So they are varying all the time. They are never completely stable. So in BE stars, we see variations all the time on all time scales from a few hours to several decades. When you look at a BE star, it will always be different from the last time you looked at the same BE star. And because they include all these physical processes, they are also a great laboratory to study stellar physics in general, because we can study rapid rotation and pulsations and flattening and everything else about the disk and the environment. So the main property of these BE stars is the presence of this very special decretion disk. And we can see this disk in the spectra of the stars in their emission lines. The emission comes from the disk. The absorption that we see in the spectra comes from the star and the emission comes from the disk. And the shape of the emission depends on how we are viewing the disk. If we look at the disk face on, or if we look at the disk edge on, the shape of the emission will be different. Can you see my mouse on the slides? Yes, maybe. So here, for example, we have the edge on disk. And so because the disk is in front of the star here, it creates an absorption in the center of the emission profile. While here we see the full disk, and therefore it's only a single peak emission. And we have intermediate states here where part of the disk is hidden behind the star and it creates a small absorption, etc. So the shape of this emission that we see in the spectra tells us how the disk is oriented. Now the disk is not necessarily homogeneous. There can be an overdensity somewhere in the disk, for example, here. And if the observer is on the left side here in this figure, depending on if this overdensity is on the left side of the star or in front or in the right side or behind, this will also change the emission profile. And in particular, if we have more matter, for example, here on the left side of the star, it will create additional or stronger emission on the left side of the spectral line. So it's the blue side of the spectral line. If the overdensity is in front of the star, it creates some kind of occultation, some kind of eclipse of the star, if you wish. And so we have additional absorption in the center, and so on. So the shape of the emission depends on the orientation of the disk, but also on how homogeneous the disk is. And as this overdensity will turn around the star, we will see the emission peaks change from blue to red and so on. So as we look at one BE star at different moment in time, we will see different shape of emission and different level of emission. So here on the left, for example, we see several profiles of the same line of the same BE star, but at different times. At the bottom, we see the synthetic spectrum of this line, so how it would be if there would be no disk at all. And in the top, we see 4 different observations at different times. This is taken 6 years apart, more or less, between the first and the last one. So in the bottom one, we see almost no emission. So there was almost no disk around the B star at that time. But then some ejection of matter occurred and emission started to build up. And you see that 6 years later, we had a lot of emission. There was a quite strong disk around the star. So the emission level that we see in the spectra depends on the outburst history, on how many ejections of matter occurred and how much matter was ejected each time. We see that in spectroscopy, but we can also see it in photometry, and that's what you see on the right plot here. This is an observation of photometry of 1b star with the Hipparcos satellite. And you see at the beginning that the level or the magnitude was more or less flat, while decreasing a little bit. That's what we call the precursor phase. But then suddenly there is a big rise of the magnitude, the stars becoming brighter, and this is a moment when it is ejecting matter. And once the ejection is finished, there is a relaxation phase where the magnitude goes back to its normal level. So also in photometry, you can see outbursts, but you get less details about the physics of the disk or the structure of the disk. So these BE stars eject matter, but how do they do that? That's the big problem in BE star research. What is the mechanism to eject matter? Of course, the first thing we think about is the rapid rotation, because we know that all BE stars rotate really, really fast. So we immediately think there must be a link between this rapid rotation and the ejection of matter. It's easy to see the rapid rotation of stars in their spectra because of the Doppler effect. So as a star rotates, the left part of the star here in blue is going towards us, coming towards us. The central part is going perpendicularly to our line of sight. And the red part here is going away from us, right? The star is rotating like that. So some light is coming at a different velocity towards us than the other part of the star that's going away from us. And so this hemisphere can be cut in vertical strips here, and each vertical strip will correspond to a certain velocity in the spectra. Therefore, the more rapidly the star rotates, the broader the spectral line. And the blue part of the spectral line corresponds to this side of the star, and the red part of the spectral line corresponds to this side of the star. Okay, so it's very easy to measure the rotation velocity of stars just by looking at the broadness of their spectral line. But in the case of BE star, not only they rotate fast, but they rotate really, really fast. And because of that, they are flattened, like here on the right side. If the star would not rotate at all, it would be just spherical. Of course, we think all stars are spherical. But as they rotate more and more rapidly, the centrifugal force elongates the equator. And for BE stars, they are not spherical at all. They are really flattened. And we could see this in reality with observations in interferometry. That's what you see at the bottom part here. All these points here are interferometric points, measurements of the surface of the star. And then you can draw the ellipse in blue here that shows what the shape of the star really is. And so this is a classical BE star Alpha Eri, and you see that is really not spherical. So how would this rapid rotation help to eject matter? Well, it's just like on the Earth. If you want to send a rocket into space, you have to have this rocket leave the Earth with a certain velocity. If you launch a rocket with a too slow velocity, it will just fall back on the Earth, of course, because of gravity. You need to launch this rocket fast enough so that it escapes the gravity of the Earth. And it's just the same on a BE star. You need to eject the matter sufficiently fast so that it escapes the gravity of the star. And of course, if the star rotates very fast, you already have the velocity to escape the star. But unfortunately, the measurements we did show that they don't rotate fast enough. They rotate at 90% of the velocity that would be needed to eject the matter. So we are close to this ejection velocity, but not quite there. The conclusion is that rapid rotation certainly plays a very important role in this ejection, but it's not enough. We need to find an additional physical process, another mechanism to bring extra energy to go above this critical velocity at which the matter will go away. And the two main explanations that have been studied over the last few decades are either the star is magnetic or it has pulsations or both. So let's first look at magnetism. Why do we think that maybe BE star could be magnetic? It is because during the 90s, we discovered that hot star can be magnetic. That was not known before. Why? Because hot stars have a very different structure than cool stars. Cool stars like the sun have a convective layer outside of the star, so that the envelope of the star is convective, and therefore they can make a dynamo and produce a magnetic field. But hot stars do not have a convective outer layer. Their core is convective, but the outer layer, the envelope, is radiative. That means there is no convection, there is no dynamo. So we thought for many, many years that there would be no magnetic field in hot stars because we cannot make a dynamo in the envelope. But at the end of the 90s, we found that, in fact, some hot stars are magnetic. And now we understand how this occurs. These magnetic fields are not produced by the star itself. They are a remnant from the magnetic field that was present when the star was formed. That means that there was a magnetic field in the molecular clouds from which the star was formed. When the molecular cloud collapsed, the magnetic field got trapped into the star. And this is why we call it a fossil field. It's a field that is a remnant from the origin of the star. And these fields, they are very simple. They are usually just dipoles, so with a north magnetic pole, a south magnetic pole, or positive, negative pole, if you wish. And the magnetic axis is simply inclined compared to the rotation axis of the star. That's all. So it's an inclined dipole. Typically, the field strength in hot star is about 3 kilogauss. As a reference, on the Earth, the magnetic field is 1 Gauss. So this may sound strong, but in fact, for a star, it's not very strong. It's much stronger inside the star. The 3 kilogauss is the strength at the surface. And we have found from surveys of magnetic fields in hot stars over the last 10, 15 years, that about 10% of all hot stars are magnetic with fields above 50 Gauss. So it could be that BE stars are also magnetic, and this is the explanation. How could this explain the presence of a disk? Well, if a star is magnetic, the particles of the winds that escape the star are forced to follow the magnetic field lines. They cannot escape in any direction. And it is easier to escape along a magnetic field line than if there would be no magnetic field. Because it is a dipole, the particles escape from the positive pole, other particles escape from the negative pole. They follow the magnetic field lines, but these are closed loops. So the particles coming from both hemispheres will collide at the magnetic equator, and they produce a disk at this magnetic equator, which you see on this figure here. So we call this a magnetosphere, but it's nothing else than a circumstellar disk in the magnetic equator. And so this could be a way to make a disk around the BE star. That was an hypothesis, at least. We can easily test this because if there is a magnetic field at the equator of the magnetic equator rather than at the rotation equator, then as the star rotates, we will see this disk under various angles, various inclinations, and therefore we will see a modulation of many quantities. For example, in photometry, we will see this disk under various inclination. It will make an eclipse in front of the star and so on. So we will get some kind of rotational modulation in the light curve. We will also see this in the spectra. We will see this in X-ray emission that is produced by the shocks of the particles coming from the two hemispheres. So this X-ray produced in the disk. We will see variation in the UV in spectral lines that are produced by the wind. And these lines are produced above the pole where the particle of the wind escape. And again, there will be some kind of rotational modulation of these wind lines. So there are many diagnostics we can use to see if we find rotational modulation, and that would be a sign that the disk is in the magnetic equator rather than in the rotation equator. So is this the solution? Well, no, it is not. We have shown from theoretical calculation that first of all, when the star rotates really fast, it hinders the stability of this fossil field. That means that it's much more difficult to make a fossil field in a BE star than in a normal, slowly rotating hot star. The field will not be stable. The star can still have a weak field, but not a strong field. And observationally also, we tested this. We made a very big survey of magnetism in hot stars, where we observed more than 500 stars, and 43 of them were classical BE stars. And for none of them, we detected a field where we would have been able to detect fields stronger than 300 Gauss. So there could still be weak field in these stars, but clearly there is no BE star with a strong field. And in fact, the B star Omega Ori is the only one for which we have clear indirect signs of the presence of a magnetic field. So we see this rotational modulation in some quantities, but we do not see a full magnetosphere, a full disk. We only see two clouds that are located at the intersection of the magnetic and rotation equator. And there is still a disk in the rotation equator, but there are two overdensities at the intersection of the magnetic and a rotation equator. So this is a star with a weak field. We've not been able to detect it directly, but we have a lot of signs that it is there. But in general, well, there is no strong field in classical B star, and this is not the explanation of these ejections of matter. Now we looked at this problem the other way around. Let's imagine that there is a disk in the rotation equator due to whichever mechanism, and we add a magnetic field, a fossil magnetic field like in other hot stars. What happens? Well, if the field is a few Gauss only, nothing much happens. The disk does not care about the presence of this field. But if the field is 100 Gauss or more, like you see in the bottom row of this plot here we have 100 Gauss. The disk is here in red, and time is passing from left to right here. Well, very soon the disk will get disrupted and it disappeared. And this is why BE stars with a decretion disk and a strong field do not exist. Because if the field is strong, it will disrupt the disk. It is not a BE star anymore. Okay, so we have to look for another explanation, and another good explanation could be pulsations. Here you see the H-shell diagram. If you're not familiar with this, it is the luminosity of the star versus effective temperature of the star. And we can put the stars here on the main sequence. So the sun would be like here, and then the star evolve to the right and become supergiants, and they end their life here, for example, if they are cool stars. Okay. On this diagram here, what is shown is the groups of pulsating stars. And you see that pulsation exists in many types of stars all over the HR diagram. But what I'm interested in here is these two blue ellipses, which are two kinds of pulsators. We call them beta Cephei pulsator and SPB, which means slowly pulsating B pulsators. And they are here in the HR diagram. But in red, I've shown the region of the classical BE star in this diagram. And you see that it overlaps. So we expect already theoretically that classical BE star will pulsate. And indeed, we've found since then that basically all BE stars pulsate. If they pulsate, we can see this in their spectra. You see that on the right side. As the star rotates, we will see the different parts of the star that move in and out of the star. They will create deformation that travel along the line profile from the left to the right. So from the blue side of the line profile to the red side of the line profile. And so if you just wait for a moment and you look at the star as time passes, you will see these changes in the line profile that are the signature of the presence of pulsation. Okay, to see this kind of deformation in the line profile, you need very good resolution and very good signal to noise, because the amplitude of these variations that you see here is about 1% of the depth of the line. So you need very good quality data. So to study pulsations, we have different ways. So with the spectra, as I just showed, or also with photometry. And nowadays, over the last, I'd say 15 years or so, we've been using mostly space photometry. So the Kourou satellite was the first one, and there was Kepler. Now we have TESS. Soon there will be Plato. It's a series of space missions that do asteroseismology, so study of pulsations of stars. And we were very lucky that the first satellite to do this, Kourou, or one of the first, there was most small satellite just before, but the first big satellite, Kourou, observed several BE stars, and one of them went into outburst during the observation. This is the one I'm showing here. So what you see on this plot is the light curve of this BE star as observed by Kourou. The vertical, what looks like noise, is not at all noise. These are the pulsation frequencies. So if I would zoom in here, you would see a coherent pattern of sinusoidal waves, but produced by several frequencies. In fact, in this star, we found 30 families of pulsation frequencies representing in total more than 300 different frequencies of pulsations. And so this produced this vertical, what looks like noise, but is not noise, vertical variations here. But we can cut this light curve in 4 parts. The first part, which I have called quiescence phase, when nothing was happening, right? It's flat on average, the magnitude did not change, the flux did not change, except from these pulsation variations. And then there is a small decrease, which we call the precursor phase, and then suddenly the ejection of matter, the outburst phase. And once the ejection is finished, we call this decrease the relaxation phase. Now, if I cut this light curve in this data set into these 4 parts, quiescence, precursor, outburst, and relaxation, I can study the pulsation of these 4 parts separately and see what happens. And this is the results. At the top, we see the pulsation frequency that we detected when the star was quiet. And there is mostly some what we call pressure modes, so this peak or this peak, plus a few other gravity modes. But then when the precursor phase started, you see a forest of peaks here that start to appear in the gravity mode domain. And during the outburst, the amplitude of this peak became really, really big. As soon as the ejection of matter was finished, this amplitude decreased again, and the P mode that had decreased during outburst reappeared. So we have certain pulsations when the star is quiet, and we have other pulsations when the star is ejecting matter. And this was the very first observational proof, direct proof, that there is a clear correlation between pulsations and outbursts. It is obvious from this plot that pulsation and outbursts are related. And what we found later on, thanks to models and a lot of work, is that the modes that are here, this forest, are not pure gravity mode. They are what we call stochastic gravito-inertial modes. So I don't want to go into the detail of the physics, but the difference is that these are modes that are produced in the convective core of the star, rather than excited by the opacity of iron in the envelope of the star. Traditionally, the beta pulsator, the SPB pulsator that I was talking about earlier, and the BE stars in general, were thought to be driven by this kappa mechanism, so the opacity of iron in a thin layer close to the surface of the star. This is true for these P modes that we see here, for some of the G modes, but we have discovered with Coro that there are another kind of pulsation that are excited in the convective core. And these modes turned out to be very important. These are the ones that are driving the outburst. So to summarize this part, the decretion disk comes from this ejection of matter, and the ejection of matter is driven by, first, the rapid rotation, which already brings the surface of the star close to the velocity at which the matter can escape, plus pulsation, this stochastic gravito-inertial wave that transport angular momentum from the core to the surface. So they bring additional energy in the surface layer, and therefore the matter can go away. Now, even if we've understood that it is rotation plus pulsation that eject the matter, the exact detail of how it works are still not known. Why outbursts occur at certain moments, not at others? Why is it not periodic, for example? It is more sporadic, every now and then there's an ejection, but it's not very regular. Why? Why do some stars have more outbursts than others? Sometimes there is 30 years without nothing happening. Some stars have an outburst every 6 months. We don't know why. We don't know the details. And this is what we want to understand now. So to understand this, we need to study all the variations of BE stars. We need to study them for many different BE stars to be able to do statistics. And we need to do that on a long term, over sometimes several decades, because we want to be able to study several outbursts and the recurrence of these outbursts. Compare, for example, to parameters of the star. For example, there's an hypothesis that maybe hot BE stars have more outbursts than cooler BE stars. Is this true statistically, or is this just an impression? To know that, we need to have enough data. So we decided that we needed to have first a catalog of all the known BE stars, and then observe each of them very regularly, take spectra very often, and see the state of the emission and the state of the disk. And each time we detect an ejection of an outburst, we want to give an alert and then ask everybody to observe these BE stars during the outburst as much as possible so that we can follow exactly the morphology of the outburst. So to this aim, we developed the best database, the BE stars and spectra database, which you can find at this address here. And I want here to thank in particular Bertrand de Batz, who was really essential in the development of this database. So BESS contains a catalog of BE stars, first of all, over 2,000 known classical BE stars. We have also added later on the stars that are called Herbig BE stars. These are also stars that show emission in their spectra, but due to an accretion disk. These are stars of the pre-main sequence phase, so that are stars that are forming still or just formed. And so this is a different kind of disk, but because they are often confused with classical BE star, we decided to put them in the database so that we can collect their spectra as well and differentiate between the two. And more recently, we've added B bracket E supergiant. This is a very weird special kind of stars, but again, they are often confused with classical BE stars, so we've added them so that we can study them separately. Sometimes we're not completely sure if they are a classical or a Herbig BE star. We have them in the catalog anyway, but it is stated that we don't know yet. So at the bottom here, you see all our stars as a function of magnitude. And the red line gives you the completeness. So we know that until about magnitude 11, all the BE stars that exist are known and are in the catalog. But above magnitude 11, we are missing a lot of stars that have never been discovered, simply because, for example, no spectra was ever taken of these BE stars. So we don't know that their lines are in emission. We don't know they are BE star. So there are still a lot of BE stars to be discovered, but on the faint end. So that's one contribution of amateur to this program. They can help discover new BE stars, and sometimes also bright one. It can happen, but mostly faint one. And to discover them, if you want to find some new BE star, you should observe faint B stars, hot stars, and you can do that with low resolution spectroscopy, it's enough. And then search for which stars show emission in their spectra, especially emission at H alpha. You see an example here at the bottom. This is a spectrum at low resolution, only 700 resolution of a B star. And here you see clearly an emission peak. There's a zoom here of this emission. Obviously, this line is an emission. If you find this, it makes it a very good BE candidate. And then you should take a high resolution spectrum, like here on the bottom, to see exactly how this emission line looks like. And then we can decide whether we think it's indeed a classical BE star or maybe a Herbig star. And if so, we can put it in the BESS catalog, but the condition is that you should publish your discovery, because every star in the BESS catalog has a reference attached to it that shows that it's a BE star. And if you just write to me and say, hey, I've found a BE star, I cannot put it in the catalog because I need something written somewhere that shows that it's true. So there are in particular two programs that are ongoing by Thierry Lemoult and Andrew Smith. And for example, Thierry has observed 1,322 B stars. And among them, he found 19 new BE stars that will go into BESS as soon as this paper is out. And Andrew also has found a few new BE stars. And they have a website here where they summarize everything they have observed, and they show all the spectra they obtained. And this plot, for example, is taken from them. So you can join their effort, or you can do your own list of faint B stars and try to find new BE stars, and we'll be very happy to add them in the catalog. Now, of course, BESS is not only a catalog of B star. What is more important is that it is a collection of spectra of BE stars. And as of a few days ago, we had 237-something thousand spectra in BESS. And that's a lot. These spectra are in FITS format. So that's a very standard format for spectra that we adopted for BESS. And we have a few extra special FITS keywords in the header that help the database to sort the data and find the data, but also help the users of the data to know exactly what has been observed and how it has been observed or reduced. In addition to the spectra, each spectrum is linked to a set of 3 records, the observer record, the instrument record, and the observing site record, so that whoever wants to use the spectrum knows where it has been taken, by who, with which instrument, which resolution, and so on. So anyone in the world can query the database, get spectra, and all the information attached to that spectrum. When you upload a spectrum into BESS, there will be first an automatic validation of the information that you're providing, especially the keywords in the FITS header. And we check, for example, that if you claim you've observed this BE star at that time, it is indeed observable at that time where you are located. Okay, this is just to avoid stupid mistakes in the headers and so on. This is done automatically by your program. But then your spectrum goes into a waiting room, if I can say, and a human, a validator, will look at your spectrum and decide if it is good and put it then into the BESS database, or if the validator finds that there is something weird, something wrong, a problem in the wavelength calibration, for example, the validator will contact the observer and help the observer to improve the spectrum before we put it into the BESS database. Basically, I can say that 100% of the spectra that are sent to BESS end up in the database, but sometimes we have to do a few iterations with the observer until we find that the spectrum is good enough to enter the database. But at least once the spectra are in there, any user can use them and know that they have been checked and that they are correct. So here you see the contribution, where they come from. Of course, many observers are in Europe because this is a project that started in France. But now we have observers really from all over the world, and this is great, especially when we do follow-up campaigns. And as of a few days ago, 74% of the spectra in the collection of BESS were provided by amateurs. And this number is increasing all the time. I remember 3 years ago, I gave a presentation during this BESS workshop that Ken was mentioning. And at that time, it was 60% of the spectra. And now it's 74% of the spectra that come from amateur. And today, there are 133 amateurs in this collaboration. So when you query the database, you get a result tables that looks like this, for example. Here I'm just showing the last few spectra that were put into the database a few days ago when I prepared this presentation. And then you can click on the spectra, either to download it if you want to use it for science or just to look at it, or you can plot it just to have a first quick look. And you find all the information, this observer record, site record, or instrument record. Of course, also information about the star itself. Now, in addition to providing spectra, amateurs have a very big contribution in the validation of the spectra. 7 out of the 10 validators of the BESS spectra are amateurs. These are all the people in the first row here, and only 3 are professional astronomers. So I want to thank them really, really much because they are doing a huge work. I remind you that there are 237,000 spectra, and they have all been validated by hand by one of us. Third, in addition to providing spectra or validating spectra, you can also analyze the spectra. For example, you have bad weather, or you don't have a working spectrograph yet. Well, you can still contribute to this project by analyzing the data collected by others. For example, we're following the variation of the equivalent widths of some emission line, HR alpha in particular. We see how the integral of the line is varying with time. So how much emission there is in the photospheric absorption line. And this is an example of plot produced by Valérie Desnoux for one BE star. And you see with these red dots here, how the equivalent width is changing with time. And you recognize 3 peaks here, more or less 4 years apart, 4 or 5 years apart, where outburst occurred. So these curves are very interesting to follow the recurrence of outburst. You can also check how the profile vary, this blue and red peak changing with time, for example. You can just work on the parameters of the star, for example, looking at the rotation velocity from the shape of the spectral line. So there are a lot of work that can be done on the spectra itself, or on themselves. Even if you cannot observe, you can contribute. Fourth, we have a best monthly report prepared every month by Valérie Desnoux, and it is published on this website and in several other places, and you can also get it by email. And in this report, Valérie keeps track of the evolution of stars and of the outbursts that occurred. And so it helps to see which stars are very active and should be observed more often than others, for example. And finally, one very important tool is ARAS Beam. This was developed in particular by Francois Cochard and Jean-Jacques Broussard. This is a tool to help observers decide which BE star observed tonight. Okay, we have more than 2,000 BE stars. If you want to start observing tonight, which one should you observe? Well, we tell you with this tool, if you connect on this website, shown here at the top right, you can put the parameters of your site, for example, and of your instrument. What is the limiting magnitude you can reach? Which declination you can observe, where you are. You can put all this information, which lines you want to observe or whatever. And then you launch, and it gives you a table of the stars that you can observe tonight with a color code that tells you which one we would like you to observe. So if it is in red, it means we're lacking spectra, and right now you should observe it. It's a high priority. If it is yellowish, yellow-orange, it means that we're still okay, but very soon we will need a spectrum. If you can do it tonight, great, but otherwise think about it in the coming days. And if it is green, someone else already took a spectrum very recently. We don't need one right now. And every now and then you will see a target that is in purple. That means that this target is into outburst at that moment. It is ejecting matter. We want you to observe it as much as possible. So this is really making your life easy when you want to observe for this program. You go on this website and we tell you what you should do tonight. Now, the goal, of course, the first goal is to acquire H-alpha emission lines, because it is in H-alpha line that the emission is the strongest, the easiest to follow, where we see most of the evolution. So this is our priority 1 line to observe. You should observe it with high resolution if you can, especially for the bright stars. But if you're observing very faint stars, we understand that you may not be able to reach a good signal to noise, and you can go for lower resolution. And that's okay too. With lower resolution, we see less detail in the profile, but we still see how the total emission is varying. Now, if you have other possibilities, it's also interesting to look at other wavelengths, for example, at H-beta. Some of the observers now even observe in the near UV or in the infrared. Every data is useful because we see different things at different wavelengths. In the infrared, for example, we can see dust that could be around the star, and that helps us distinguish between her big star and classical B star. And if you discover an outburst, then great, you're a hero for the best community. Please tell everyone, alert the community, and then we will start a follow-up campaign where everybody starts observing the star as much as possible. At the bottom here, you see an example of the variation of emission at relatively low resolution for a B star. So you cannot read the date, so I've highlighted 2. It goes from the left to right, and then the second row continues. And here it was the 30th of June, where emission started to rise, and then we had stronger and stronger emission. And here in October 18, it was really low again and almost nothing. So within a few months, we saw the full outburst. I want to show in particular this example of V442 AND, which is a star now in our community, I think. Now, it's a star that goes very regularly into outbursts. So many of the best observers were lucky to find an outburst in this star, and we had several follow-up campaigns, and this is one of the campaigns organized by Olivier Teyssier, and you see all the spectra that were collected by many observers and how the H-alpha profile changed with time, and you see here, oops, he has made this into a very nice plot. And so we have regular campaigns on this star each time it goes into outburst. And it has become a bit of a candle star, if I can say. We have a great data set, and many complementary observations were obtained, including by a professional astronomer, and including, for example, on the Hubble Space Telescope. And this was all driven by the fact that the BESS community discovered that this star is going very frequently into outburst. So indeed, we often now have campaigns between BESS observations and other facilities. I already mentioned the CoRoT satellite. When we were observing with CoRoT between 2003 and 2009, each time we had a B star observed by CoRoT, we were asking the BESS observer to also take spectra. And this has been really very useful because it helps us to interpret the light curve observed by CoRoT. So for example, this is another light curve for another B star. Again, this is not noise, this is pulsations, but you may see three places where I've put these purple arrows where the light curve departs a bit from the average trend here. These are minor outbursts, so small ejection, little blobs of matter that went away. And at the top, you see spectra that were collected during these observations. In red and blue, these are the periods where we had requested a spectra on the professional facilities, so with ARAS at AAVSO and SOPHIE in France. But in green, you see all the spectra that were taken by amateurs. And as you can see, we were very lucky because for 2 of these events, we did not have any professional spectra, but we had a lot here of amateur spectra from the BESS database. And so we were very happy to have those because we could interpret and confirm that this was a minor ejection and not just a problem in the data, for example, in the code. So it's very important when you do photometry to have simultaneous spectroscopy to better interpret the light curve. Now, another one, now I want to go more into those that are ongoing because maybe you want to join those programs. So another one is a program together with CHARA Interferometry. This is a campaign where we ask BESS observer to observe a few very bright BE stars and wait until they see an outburst. And as soon as they see the very beginning of an outburst, even if they are not sure, as soon as they see that maybe some emission is appearing, they should alert the CHARA team, and the CHARA will point the CHARA facility on the star and observe in interferometry the very beginning, the very onset of this outburst. That's the goal of this program. We want to see with interferometry the very, very beginning of the ejection.
Coralie,
Yes.
I'm sorry to interrupt. This is Ken. We probably have about 5 more minutes available.
Good, I'm almost finished. Thank you. So this is a collaboration led by Robert Clément. It's interrupted right now because of the Bobcat fire. Unfortunately, as you may know, there has been a lot of fire around the CHARA facility and it had to close down. Of course, we are lucky that it did not burn, but the program and the observations there were stopped. It will resume very soon. Another one that's ongoing is observation together with the TESS telescope. So that's another satellite for asteroseismology. And this star observes many, many stars during periods of 27 days. And in fact, it includes 432 BE targets. And we requested that for each of these targets, we try to take observation over the 27 days of observation by TESS. So that's a lot of observations. We are making priorities, of course, because we understand we cannot follow all of them, but this is a program that's very active and ongoing, and you can join if you like. Here you see an example of a TESS-like curve of a BE star. You see how active this star is, how many events there are, and of course, to interpret this light curve, we really need to see the level of emission and the shape of the emission. So we need to have spectra everywhere here to understand this light curve. So the goal is to obtain 1 spectrum per night for each target during 27 days. And so finally, I want to say that, of course, all this work is being published. There are 2 publications that describe BESS itself, but there are, as of yesterday, I think, 99 publications using BESS data. And many of them have amateur co-authors, of course, because each time many observations of one amateur are being used, we ask the author to add these people as co-authors of the paper. But what I find a bit a pity is that very few of these papers are led by amateur. It's very rare that the first author is an amateur. And that's mostly because amateurs are a bit too shy or too humble. And I want to push each amateur here to please publish your results. Don't hesitate to be the leader of a paper, and have professional amateurs, professional astronomers as co-authors, but you can be the first author, even if you're an amateur, if you've done the work, right? And so the bottom here is just the very last paper that came out very recently. It's a 2021 paper even, with best data included. So just to conclude, I want to summarize, say that BE star are great laboratories for many physical processes. And we need to better understand how they eject matter, so this BE phenomenon. They are very interesting to observe in spectroscopy because they vary all the time. Each time you observe one BE star again, it is different. So it's really not boring work. And the BESS database has allowed to structure the community, this pro-amateur community, around many projects and around this database, and also to easily disseminate the data among the professional astronomers. Now everybody knows the BESS database. Everyone in the BE community, professional community, knows this database, and when they study a star, they have the first idea to go on BESS and see if there are data. So don't hesitate to join our community, even if you are a beginner in spectroscopy. In fact, it is very good if you're a beginner to join this project, because with this system of validation of the spectra in the database, we can help you improve your process for observation and reduction of the data. So please join us. And as Ken said, it's all fun and science. Thank you.
Thank you very much, Coralie. That was an excellent presentation. I know I really enjoyed it, and I'm sure everyone else did too. And just on a personal note, I would emphasize Coralie's last point there, that if you are just getting started in spectroscopy, this is a great way to learn and a great way to get better. So definitely take a look at the BESS program. So we have several questions, probably only have time for a couple, but I'll start with the first one, which is there any relation between planetary ejection and BE star ejection?
Planetary ejection, no, there is no relation. So in BE star ejection, so we're not ejecting the BE star, you understand, we're ejecting matter from the surface of the BE star into a disk. And this is the process I described with rotation and pulsation. Planetary ejection is completely different. This is during stellar formation, and no, it is really not related.
Okay, thank you. Second question was, how does a BE star maintain a fossil field if it lacks the capacity to generate a magnetic field on its own?
Oh, that's a very good question. Yes, so it is not producing the magnetic field. The field was there when it was formed, and it got trapped. And once it is there, it relaxes onto this dipolar configuration, and it is stable. And so because of the principle of magnetic flux conservation, the magnetic field will remain there. It cannot disappear. But what happens is that as the star evolves, the radius of the star becomes bigger. And because magnetic flux is conserved, the magnetic flux at the surface will decrease as the square root of the radius. So when the radius of the star increases by a factor of 10, the field strength at the surface decreases by a factor of 100. So the field that we observe seems to decrease with time, but in fact, the field inside the star is still the same. It's just the radius of the star that increases. So it's just the stability of the field in the star and the principle of magnetic flux conservation.
Okay, thank you very much, Coralie. I think we're probably about out of time at this point, but again, it was an excellent presentation. I know you're super busy, and we appreciate all of your time and all of your help. And this is a wonderful program for people to know about. So thank you.
You're welcome. It was a pleasure to be here.
Up next on today's presentation is Stella Kafka. I've mentioned Stella before last weekend, and this weekend, Stella is the executive director of the AAVSO. She's also an astrophysicist, And she's going to be talking to us today about the AAVSO spectroscopy programs and what all is happening there. So welcome, Stella.
Thank you, and welcome you all again at the workshop here. It's such a pleasure to see people from all over the world joining us today. I would like to start with a comment based on what Coralie just said, that everyone should feel comfortable actually doing their own spectroscopic analysis. So if you have your own spectra and you have the opportunity to do research, please don't hesitate to ask help from professional astronomers, from your colleagues, to write your own paper. And actually the journal of the AAVSO, JVSO, is also accepting manuscripts on spectroscopy. It's a double-blind referee journal, which means that you don't know who your reviewer is, and the reviewer doesn't know who you are. So we are removing any biasing from the reviewer's point of view of who is writing the manuscript. So if you want to have if you have a nice result and you would like to publish it, write it up, send it to our journal as well. Consider our journal as another avenue for publication of your results. I'm sharing my screen, right, Ken? It's always good to confirm.
Yes, you are.
Awesome, thank you. So when I was given this subject to give a presentation at this particular workshop, I was told to talk about anything I wanted. That's a very, very dangerous freedom to give me, because I can talk about many things that the AAVSO has in progress, I was working on. So I chose to actually confine these presentations to two different subjects. I would like to talk about the AAVSO Spectroscopy database, a little bit about what it is, what it can offer to you. And also I would like to give you a quick tour of various variable star cases, highlighting interesting features that you can explore with your own spectrograph. There is something for everyone, depending on your spectrograph resolution, your time, your interest. You can find appropriate stars to study. So please take a look at whatever you would like to do. There are options for your science. Before I start actually talking about the AAVSO spectroscopy database, I want to give a big shout out to Coralie. When I first met her about 6 years ago, and I heard a talk from her about all kinds of aspects of the BEST database, I was so impressed that I actually had very, very detailed discussions with her how the BEST database is working, what it offers for its community, how the validation process works, how she's making sure, she and her colleagues make sure that the data that get in the database are of the quality and of the value that the professional astronomical community, or anyone who wants to do a project, an educator, a researcher, a citizen scientist, can actually just download the data and do the research themselves without questioning the quality. And she gave me so many useful tips. So what you're going to see as part of the AAVSO spectroscopy database, AAVSpec, is actually based on this discussion. So there are lots of items that are duplicated. You can find the AAVSO spectroscopy database from the observing section. So this is the leading page of the observing section. Right now, we have more than 4,000 validated spectra. This database is an open access repository of variable star spectra that comes from our observers, which actually complement light curves from our photometric database to provide a very unique picture of various phenomena of interest to the AAVSO community. And the main idea is to build a long-term baseline of spectra and light curves and photometry to understand some very puzzling phenomena in nature. The format of data accepted in this database is the same as BEST. We're talking about one-dimensional fields file with a header that has specific keywords that are required for the database. And of course, we are focusing a lot on the validation process here at headquarters. Actually, I am one of the prime validators, so every spectra come to me before it gets in the database. And we do have an avenue of providing feedback to observers based on the quality of their data. And you'll be surprised, sometimes even the most experienced observers don't notice little issues with their spectrograph and submit data that you know, a second pair of eyes can actually catch an error and correct it later. So you can access, as I said, you can access the database from here. And this is what you see when you get there. The first page shows you pretty much the recently published spectra. So if I am to zoom in the menu that you can find here, you see these different tabs, that different options. So starting from the very beginning, at the recent, you can see the top 100 objects that are submitted to the database and explore their properties. So you can see the ID of the spectrum when it was observed, when it was uploaded, the observer code of the individual. You can get information on the star itself, what kind of equipment or observatory telescope the observer has used in order to take that particular spectrum. This is a spectrum of P Cygni. It's a cataclysmic variable in outburst that was submitted quite recently as an example. You also see a button here that takes you to a way of retrieving data. You can actually search by location, the coordinates in the night sky, by observer code. So if you want to see the spectra from a specific observer, you can search from here. Of course, you can search by object name, or object type. So at some point, you can mine the database for a specific object. And then, of course, I would like to attract your attention to the photometry database that we have. So you can actually go there and see the light curve and the spectra at the very same time. Moving on, here is the link to submit your own spectra. Here is a way of discussing your spectra. As Coralie mentioned, one of the valuable aspects of this kind of projects that we're building a community. And we are building communities, international communities of individuals discussing science through our forums. These are ways for our community members to actually discuss all kinds of aspects of spectroscopy in this particular case, such as observing campaigns, science results, specific stars to be observed, or ask questions about instruments, software, and interact with fellow spectroscopists and actually learn and grow together. Moving on, you can get actually information on your own spectra here, such as your tally of observations, the number of downloads of your spectra, the average download per observation. So this is a way for you to actually keep track of your own spectra. And moving on, here in the help, you can find all kinds of documentation that can help you actually learn more about the database itself. So what you find there is the manual of, there you go, the manual for spectroscopy that we have, the AAV spec itself, user manual, some frequently asked questions, even a quick guide if you want just a checklist of when you're observing you're taking your spectra of how to move forward with the procedure itself. And of course, everything can be accessed by from WebObs, which is our main submission webpage. So from this is a very quick tour. Please visit our spectroscopy database and play yourself and check out the different tabs. I would like to move to the science and talk about what kind of projects you can pursue with your telescopes and equipments and what we measure when we're doing this kind of scientific projects. And I will start with a refresher from what we talked about last weekend, a little bit of the principles of spectroscopy. So we have three main principles of spectroscopy based on which we are assessing properties of data. Wien's law is the first one that tells us that objects of different temperature emit spectra that peak at different wavelengths. So hotter objects emit more of their radiation at shorter wavelengths, so they appear to be bluer. Cooler objects emit most of their radiation at longer wavelengths, so they appear to be redder. And also, at any wavelength, a hot object radiates more, so it's brighter than a cooler object. So this is pretty much the bottom line of Wien's law. It tells you that the wavelength of maximum intensity is inverse proportional to the object's temperature. So again, bluer objects go this way, redder objects go that way, bluer objects are hotter. As simple as that. The second one is Kirchhoff's laws. So like Kepler's laws of planetary motion, these are empirical laws. So what that means is that they were formulated on the basis of experiment. So what Kirchhoff's law says is that a hot gas under high pressure gives off a continuous spectrum. So if you have a gas, you have pretty much a black body shaped curve, as simple as that. Now, if you take the same gas and you lower the pressure, then you will have an emission line spectrum, something like that. If you want to complicate your life a little bit, then you have a source of continuous spectrum behind a cool gas under pressure. So in this case, what you have is a combination of these two particular spectral profiles in this particular case. Now, third principle spectroscopy, the Doppler effect. Coralie mentioned a little bit about the Doppler effect. It is actually a wavelength shift between emitted light and received light when an object and an observer are moving with respect to each other. If they approach themselves, the shift is towards the blue. If we're moving away, it's towards the red. So it allows us to measure radial velocity, rotational speed, and all kinds of velocities in stars. And it's actually key for binary star systems that we're going to talk about a little bit later. So yeah, and it can actually be measured with this equation. So delta lambda is the difference in the wavelength of an object with respect to its rest wavelength. Lambda is the rest wavelength, c is the speed of light, and the velocity, or radial velocity as we call it, is being measured here. So you can resolve this equation and get your radial velocity. So if we take all of this together, what kind of information do we get? And I'm going to get right to the measurements of spectra. We have three main quantities when we see a line profile. We can measure the radial velocity, as I mentioned, which is a deviation of the spectral line of interest from its rest wavelength. So it indicates how fast an atmospheric layer or a star that is represented actually by this spectral line is moving towards or away from us. Now, if the rest wavelength again is characterized by lambda, then the velocity is calculated through this equation. C is the speed of light. The second quantity is what we call line equivalent width, W, which actually in principle tells you how much flux is in the line. This is a measure of the area of the line in a plot of intensity versus wavelength. So this is pretty much what we call equivalent width. And technically it's found by forming a rectangle with a height equal to that of the continuum emission and find the width such that the area of this rectangle is equal to the area of the spectral line. And then full width half max, exactly what the name says. You find the maximum intensity of the line, then go to the half height of the line and measure the width of the line at that particular intensity. Now, what kind of information do we get from there? We can get information on what type of chemical elements exist in the object of our interest. Remember Kirchhoff's laws? Imagine that chemical elements are like barcodes, similar to the unique barcodes that you have in common products in the supermarket. So for example, let's take a barcode on a bottle of water. We all know water bottles, how they look like. When we go to the cashier to pay for the water bottle, then the cashier scans the barcode and the computer identifies that this is a bottle of water. So what does the computer look at when it comes to scanning the barcode? It looks at this code and the thickness of the line, the spacing between the lines, so how far away they are from each other, and the grouping, that the fact that all those lines need to be present at the same time. It's the same thing with chemical elements in stellar atmospheres. Each chemical element has its own barcode. So when we are looking at the emission or absorption lines, we're looking at very specific elements. We're looking at the strength of the line, so how thick it is. We're looking at the spacing between lines, how far away they are, similar as a barcode. And we make sure that all the lines are present. What I'm showing here is an example of 4 different elements: hydrogen, helium, mercury, and uranium, with the characteristic barcodes. They're all extremely different, very, very unique. And actually, I'm hoping that Tom Field's going to show a little bit later this beautiful, beautiful poster. It's a table of emission spectra of all elements in the periodic table that I absolutely adore, because it actually showcases all the different barcodes for all elements in the atmosphere. So this is a way that we can actually see that different elements exist in a stellar atmosphere just by looking at those barcodes, and or a combination of them. So you can say there's hydrogen, there's helium superimposed to each other. The second thing that we do is looking at outflows, winds. These are results of stars either expelling some of the outer layers for whatever reason and surrounding themselves with a shell of materials. And to diagnose them, we're looking at the shape of specific line profiles. So the reason behind the shape, again, it's based on the principles of Kirchhoff's laws. So this is what's happening. Say that we have a star, seen here, that is embedded in a gas cloud. And this is your observer in this location. Then she will see several superimposed phenomena. She will see absorption from the gas in front of the star. This is A. And she will see superimposed emission from the gas components themselves, B and C. So you put these two together, then pretty much she will see a very characteristic line profile, what we call a P Cygni profile, which is actually a telltale of outflows from stars. Here's a third thing that we can do. Again, what Coralie mentioned, the Doppler effect, rotational velocity. It's what we call rotational broadening. It's a result of actually broadening lines as a result of rotations, the Doppler effect, with respect to when the star is not rotating. So the faster the rotation, the broader the line profile. So how do we combine? How do we learn combining all these properties? What do we learn from different types of stars? And actually, the AAVSO Spectroscopy Observing section has specific recommendations on targets based on different resolutions. So I would like to actually remind you, this is a webpage where you can actually go and find different science cases, most of which I'm going to discuss here. Number 1, we can study chromospherically active stars. These are stars that have very active chromospheres, like our sun. They have large spot regions, flares, coronal mass ejections, etc. And we can see variations of the intensity profile of a spectral line due to cool spots on the surface. If you're actually lucky to detect a flare, they can see a huge increase in the continuum of your spectrum. Lines of interest in this case are Balmer hydrogen lines in emission, calcium H and K, which is chromospheric emission, the outer layer of the atmosphere, both in emission and absorption. And this is an example. This is HR 1099. It's a K2 giant. It's what we call an ARAS convent star, fast rotating, really active big giant star. The left diagram showcases in the H alpha line profile as the star is rotating. So you can see a distortion in the spectral line profiles due to rotation and due to cool spots in the stellar atmosphere. The bottom plot here showcases changes in the calcium H and K lines. You can see emission superimposed on absorption, and you can detect changes in the lines of the strength of the lines, the equivalent widths of the lines. Case number 2, pulsating stars. These are intrinsic variables, as the variation in brightness is due to physical change of the size of the star. So these are big, big giant stars that expand and contract with time. And they are a telltale of a specific stage of stellar evolution for the stars. What do you see? The spectral line changes in this case is due to periodic expansion and contraction of various atmospheric layers, usually the outer layers. Lines of interest in this case are the hydrogen Balmer lines. And this is an example of RR Lyra itself. It's a beautiful, beautiful example that I borrowed from Christian Buell's webpage that showcases that, and this is the light curve. It showcases at different parts of the light curve, different snapshots of spectra. This is the H alpha line. And the the green line here shows the rest wavelength of H alpha. So as the star is expanding and contracting with time, you can even see the minimum of the line moving towards red and blue wavelengths. It's really wonderful. It's really beautiful, actually, to measure this kind of radial velocities. And you can see even changes in the shapes of the line because of different atmospheric layers going up and down. Case number 3, binary stars. This is our case study for the Doppler effect. When the inclination of the binary is such that the orbit is close to parallel to the plane of the line, and here's your observer again, then she sees lines that are moving back and forth as a result of the 2 stars moving around the center of mass. What you can do then is resolve lines, the barcodes from the specific emission or absorption lines, and build what we call a radial velocity plot. So you can track the motion of each of the 2 stars, the velocity of each of the 2 stars as they come towards and away from you as an observer with time. So this is very valuable to us, especially in stars where you cannot resolve, where the inclination is such that you can actually not resolve eclipses. So this is another way of studying binary star systems. And this is an example. It's an H alpha line of BF Lin. The 2 components showed at different parts of the orbit. So you can see the different components as they cross each other as the star is moving towards and away from the observer, towards and away from us. Of course, B stars, I'm not going to even touch that. I'm going to tell you that go to the best database. They have all kinds of fantastic targets for observers to observe, great opportunities for people to be involved. You heard all about it from Coralie. Moving on, massive hot stars, Wolf-Rayet stars. These are extreme cases of very massive stars. They're literally shading part of their outer layers in spectacular winds. This is an example of one of those. It's Eta Carina, which is actually a binary star system embedded in a really deep nebula. What we see is the combined luminosity of the 2 systems. And actually, if you think about it, the combined luminosity of the 2 stars is greater than 5 million times that of the sun. So it's a very bright system, very dynamic system. What you see from here is very strong emission lines, most of which are coming from a nebula. This is ionized carbon and helium, helium-2 in this particular case. This is a different Wolf-Rayet star, Wolf-Rayet 137. This is the spectrum of it. It has very weak hydrogen lines. Maybe you can see H delta. This is actually a really good target. This kind of stars are very good targets for low resolution spectra. So you can go fainter, but you can see all these huge, massive nebular lines that are changing very dramatically with time. Moving on, cataclysmic variables, symbiotic stars, novae. So these are binary star systems, and spectra are actually helping us understand a little bit more accretion physics. These are some of actually the most complicated and very rewarding objects, very near and dear to my heart. These binaries consist of a white dwarf, a very dense star of the mass of the sun, and the size of the Earth. So it's a very compressed star that is literally cannibalizing its companion, which is usually a solar type star or a little bit less than the sun, perhaps a K star, through an accretion disk. So in this particular case, we can study all kinds of phenomena that has to do with the 2 stellar components themselves and their interactions. What we can see is spectral lines that can come from the accretion disk, which is usually dominating most of the line, or what we call a hotspot, which is a part of the accretion disk where the stellar stream, as it goes from one star to the other, is actually hitting the disk. You will see irradiation. So the white dwarf is a very hot star that is actually blasting its companion with irradiation. So this part, the inner part of the star, is actually really glowing, really very bright. You can see sodium D that can come from the star itself, the donor star itself. So this way you can actually study the motion of the system. It's a binary star system, so at least we can trace one of the components is moving around the common center of mass. Of course, accretion disks, in this case, material goes inward inside the accretion disk as opposed to outside in B stars. And these are sites of all kinds of cataclysmic phenomena, most popular of which are novae. So novae eruptions are the outcome of the white dwarf growing in mass in a really very dramatic way, to the point where the mass cannot be incorporated in the atmosphere of the star. So it builds a blanket around the white dwarf that reaches extreme temperature pressure, resulting to it expelling that particular blanket around the white dwarf itself. So this is a bright eruption. There's lots of material around it. And it's a very, very popular, actually, phenomenon to be studied photometrically by AAVSO observers. But when it comes to spectra, you can see such dramatic changes in the spectral lines, especially hydrogen spectral lines, when one of those stars is in eruption. The cool thing about that is that they're very, very bright. So this particular nova that went off a couple of years ago went all the way up to 3rd magnitude. So you could definitely see it visually. So if you have a high resolution spectrograph, you can actually get details in the spectral lines of these particular stars in outbursts. So please keep an eye on those. We are having alerts from the AAVSO alert system every time an interesting object is going out, and we are asking both for spectroscopic and photometric data. And the last category I want to talk to you about is supernovae. Supernovae are very far away, so they're tricky targets. However, they're also very easy targets, especially when it comes to acquiring spectra that are very, very valuable and key for the classification. What we do when we classify supernova is detect the presence or absence of certain lines. Based on that, we classify them in various categories. The ones that are much more interesting for astrophysical purposes, that determine distance or determine cosmology, are the type 1A, supernova type 1A, that are actually results of a very catastrophic thermonuclear runaway at the very center of the white dwarf in a binary star system, like the ones that we discussed before. So what are the characteristics of these 1As? These 1As have no hydrogen in the spectra, and they have silicon. So when you're observing them, all you're looking for is the lack of hydrogen and the presence of silicon. And you can definitely do that with very low resolution spectra. You don't need very high res in order to actually find these two characteristics. So with that, I would like to end my presentation and actually remind you that next weekend during the AAVSO conference, the main meeting, we have an observing section meeting for spectroscopy observing section. So if you would like to discuss more opportunities for engagement for specific targets, specific projects, how to use your spectrograph in order to pursue different science cases, I would like to encourage you to come. All I did today is to give you a glimpse of what you can do with your spectrograph and how you can find support through the AAVSO. A final thought. I can't emphasize enough what everybody else is emphasizing. Spectroscopy is really fun and very rewarding and provides a very unique information of variable objects. And I hope that this workshop will be the starting point for you to get started with spectroscopy or join projects of your interest. So with that, I would like to thank you for your attention. Wish you clear skies, hope you're staying safe, and perhaps we have time for a couple of questions at this point. Maybe, maybe not.
I think we do, Stella. We've got time for a couple here. We have one from Conrad who says, for Stella, on the main page for spectroscopy, there is a section, program priorities, recommended targets and projects. Has it been updated lately?
The answer is yes-ish. Some of the targets have been updated based on individuals who are requesting targets. Okay, and we have another question here from Richard. I'm in the process of learning my equipment and data reduction software. I'm making Prices My Standard Star Spectrum was accepted by AAVSO and made first submission this week. I have an ALPI setup and would like to have a systematic
program with AAVSO to follow up, maybe find new BE stars, or any suggestions?
Okay, Richard, there are 2 points I would like to make there. First, congratulations and welcome to the AAVSO spectroscopic database. Second, for BE stars, I will wholeheartedly send you to our colleagues in France. I'm hoping we're going to hear more from those individuals. We're going to hear from ALPI soon again, right, Ken? Is it today, tomorrow? What you can do with ALPI spectrographs?
We're going to hear more tomorrow.
Awesome. So for BE stars, please contact Coralie. The BEST database is an amazing resource if you want to actually get involved with a project like that. For other objects, I would like to know how bright, how big your telescope is, to know how deep you can go with your spectrograph. And from there on, we can definitely discuss more projects. Please do contact me with this information and we'll go from there. There's so many targets. You can definitely build your own program.
Okay, and one final question for you. I seem to recall that AAVSO has a mentoring system, correct?
Yes. Absolutely. Feel free to use it. That's why we have our mentors here. Also, you know, one of the things that I really enjoy, we are at the beginning of our spectroscopy database. We launched it officially about exactly a year ago. So we have almost 5,000 spectra, actually, to be honest. I was validating spectra yesterday in there. One of the things that I enjoy personally is actually being a mentor to our spectroscopists, because we have about 45 individuals right now. So I'm building relationships with those individuals. We have really very interesting discussions. So we can definitely find a mentor in spectroscopy for you if you are looking for someone, or we can have a discussion on how to improve your spectroscopy.
Okay, great. And then finally, before I turn this back over to Lindsay, I want to read something that Nancy Morrison posted in the chat section before, when we were talking about BE stars, which was the AAVSO welcomes papers on BE stars with amateur and professional authors, free of charge to AAVSO members, quality editorial process. So please keep that in mind, everybody. You can write papers and have them published.
Yes, and Nancy Morrison, for everybody's benefit, is our editor-in-chief.
Yes.
So, and Professor Morrison actually is a fantastic spectroscopist. So we do welcome spectral data at the journal. Yeah.
Okay, thank you very much, Stella. That was a great presentation. Lots of really good information, and hopefully people will take advantage of what's offered by the AAVSO. Now I'm going to turn it back over to Lindsay to tell us about our sponsor.
So right now we are at a break and our sponsor is going to come later. Our break will be our break will be ending in 10 minutes at 20 of the hour. And then when we come back, we're going to have some more presentations. So everyone can go grab their coffee, snack, whatever you're going to do on your break.
All right, everybody. See you in about 8 minutes. Thank you. Hello, everyone. I just noticed here on the chat that Coralie is available to answer additional questions that were left over from before. And we have a couple of minutes before we start with Lauren's presentation. So let me take a look here and see what's up next. Ray wanted to know on slide 17, Coralie, what is the frequency of C divided by D, and what those refer to?
This is cycle per day. C means cycle and D means day, cycle per day. So that's the frequency, so the pulsation period, or the inverse of the pulsation period. How many cycle of pulsation do we see in one day?
Okay, thank you. And Patrick wanted to know, is it possible that our solar system evolved by means of mass ejection of matter from the sun 3 billion years ago?
Our own solar system, well, this is a very different star. Of course, the sun is a cool star with a very different structure, very different physics. It does eject matter sometimes. These are the coronal mass ejections that sometimes perturb our satellites, for example, but this is very different from the outbursts we see on BE stars, where the amount of matter on the BE stars that is ejected is much, much larger. So these are two very different phenomena.
Okay, thank you. And then Gum had a question, is it possible to share raw data, referring to the BE data of spectra, to do some training?
Oh yes, that is possible. So in the BEST database, we store the FITS reduced data, but I think many observers are ready to share the raw data, and there are some data sets, in fact, for training that we use in some schools for spectroscopy. And I'm sure that at the OHP schools, for example, they also have data available there. So yes, of course, if you wish to have some data, I think this is not a problem. We can share some.
Okay, great. Thank you very much, Coralie, for coming back in and answering these questions. I appreciate it. Next up on our schedule, we have Lauren Herrington. And Lauren is known as the tie-dye astronomer. And if you've ever been around Lauren, you know why. She's probably wearing tie-dye shirt today. And I first met Lauren last year at the Sacramento Mountain Spectroscopy Workshop in Las Cruces, New Mexico. And Lauren came into that workshop with about 80 people and immediately just captured the attention of everyone there. She was so enthusiastic, so positive and upbeat about everything that we were doing. And it was a great experience for all of us to get to meet Lauren and to spend time with her. And since then, Lauren has been doing some very interesting work that I'm going to tell you about. But she's been involved in developing what she calls drift scanning spectroscopy, which is a low-cost way of doing spectroscopy. But to my knowledge, there's nobody else doing what Lauren is doing right now. So with that, I'll turn it over to her. And I think you're going to find this presentation very interesting. Thank you.
Thank you very much, Ken. All right. So SMSW2, you just mentioned that to everyone. And I know that a lot of people in the audience probably were there and will recognize me by the tie-dye alone. That was a life-changing experience for me, that conference. Before I went there, I just didn't know that amateurs could do spectroscopy. I knew professionals, obviously, they've got the huge scopes with the big trusses, they've got the fiber-fed spectrographs, but then I didn't think I could do that, not little Lauren in the backyard with her 8-inch daub. And then I went to SMSW2, and all of a sudden I'm surrounded by 80 living, breathing examples of amateurs taking awesome spectra on their own. And not only that, not only was everyone there an expert on the subject, at least from my perspective, but it was the most welcoming group of people that I've ever had the pleasure of meeting. And I just know I learned more in those 3 days than I would have in the next 3 years otherwise. Despite how awesome Fest SMSW2 was, I do remember sitting there and feeling so close and yet so far, because now I had some of the knowledge. I had a little taste of what it would be like to take my own spectra. And yet I still didn't feel like I could do it. And the reason is because it seemed like everyone around me had something like that. But all that I had was this. And that right there on the left, you can take some fantastic spectra on that. But with just a DSLR, people told me I could use that and take some great spectra. And I gave it a shot when I got home, but it just, oh, hold on. That was not the slide that I meant to show right then. Well, I had a Daub at home and I wound up using that because when I went home and I took my spectra using a DSLR, I got some results like, okay, hold on. I'm sorry about this, y'all. Yeah, this one. Okay. View, present, all right, there. So I got some results like that. There we go. Okay. It was basically just noise, the spectra that I got using my DSLR. I had one emission line when I pointed it at EZ Canis Majoris, spent a long time shooting tracked exposures of 30 seconds on a little miniature tracker that I had. And it wasn't what I was looking for. If EZ Canis Majoris, which is like 6th or 7th magnitude, I spend nearly 30 minutes on it and I get something like that, that didn't make me happy. Luckily, I didn't believe the age-old adage of spectrography, which is that you need tracking. Everyone knows that you need tracking, and that's what I had this slide in there for. It seems like there's an unspoken rule that says that Daubs need not apply because you need tracking. You need to gather all that light. It's true. You need a lot of light to get a good spectrum. That's your number one goal in spectrography. I heard that said at SMSW2. Your number one goal, get as much light as you can into the spectrum. It makes sense. Without tracking, I mean, you're limited to short exposures. That's a lot less light. But there is a huge difference in the amount of light that a DSLR can collect and a Dobsonian can collect. And so using my 12-inch Daub without tracking, when I revisited EZ Canis Majoris, I was able to get in under a minute a spectrum that was just orders of magnitude better than anything I'd ever managed to get with my DSLR. So working on that principle, which is that larger aperture can facilitate taking spectra without the use of tracking, I kept pushing it, I kept improving it, and in the end, this is my spectra rig. It's pretty simple. There's just, I got a camera to control, or a laptop to control the camera. I got a magnifying finder scope, which I've found helps whenever I'm looking for a target that's fainter than naked eye, because the sensor on the camera is pretty small. You have to be pretty precise when you line it up. And I have an 8-inch Daub, and that's it. So when you go to make your own drift scanning rig, what you're going to want to assemble is a camera. This one right here is a cooled astronomy camera because that's what I have. Now, you don't have to have one of those. I think you can use a webcam. I don't have one personally to try out, but you should be able to. I've used uncooled planetary cameras as well, and that works well. Then there's some spacers. That's what all of this over here is. This says Barlow lens on it, but it's actually just the tube from a Barlow. I took the actual lens part out, so it's just acting as a spacer. Over here, we've got the 3.8 degree prism that the manufacturer of the star analyzer sells. I'll talk some more about that in a moment, but both the spacers and the prism are just items used to enhance your resolution. They are not required for this method, okay? So right here on the end, screwed onto the prism, is a diffraction grating, the Star Analyzer 100 diffraction grating. It's just a grating in a filter cell, and that is required. So the only things that are required for this method are a camera, a diffraction grating, and a Dobsonian or other telescope. You can use any telescope, but large aperture helps. Okay, so when you point your telescope at the sky, if you're not tracking, you're gonna see something like this. All right, so because you're not tracking, the rotation of the Earth drags the star and thus its spectrum across the field of view fairly fast, depending on your focal length. There are 3 possible methods that you could use to record that spectrum. One is that you could take a snapshot, just like a single one of these video frames. That would be pretty noisy. There's not enough exposure time in that. So I'm just gonna go ahead and throw out that method. We're not gonna use that. The second method that you could use is to take a single long exposure, allowing the spectrum to move within the frame. And that works pretty well on bright stars. It looks something like this when you do that. However, it only really works on bright stars. If you want to go for a faint target, like here's one of my favorite targets to shoot, Wolf-Rayet 137. That's this spectrum right in here. It's got some nice emission lines that you can see, but unfortunately it is sandwiched between 2 brighter stars. And if you try and take a long exposure of that, longer than just a couple seconds, you'll get something like this. Unfortunately, there's just too many other stars, too many other spectra in the field, and Wolf-Rayet 137 spectrum is lost. So that brings us to the third method, which is something that I call drift scanning. It's where you shoot a video of short exposures so that the motion is frozen, and then you stack those short exposures together to get the cumulative exposure time of one of these long trail shots. So step number 1 in drift scanning, when you go out to set up, besides, you know, just carrying your equipment out, set it on the ground, you're gonna put the grating onto the camera, and you need the grating dispersion direction, the direction in which it creates the spectrum, to be aligned with the horizontal direction of the camera. So here is what that looks like. I have my grating put onto a Barlow, just a Barlow tube. And I did that because it gives me finer control. I'm going to play that again. It gives me finer control over the rotation of the grating, larger area to grip onto, and there's more friction between the nose piece of the camera than just unscrewing the grating. So one more time, when you watch through the scope, as you turn the grating, it rotates the star and its spectrum around each other. You want the spectrum to wind up perfectly horizontal in the field of view. Okay, now, once it's perfectly horizontal in the field of view, you're done. You're never gonna have to change that unless you add some spacers or something that will rotate the grating. But if you don't disassemble the camera, then you're never gonna have to adjust that. So that's good news right there. Next up, you are going to rotate the camera within the focuser of the telescope. So you point it at a bright star, and then as the bright star drifts, it's going to draw out an angle. That's what I've highlighted here in red. That angle is the exact angle by which you need to rotate the camera within the focuser to make the star drift straight down. If you watch the green star, you'll see how the field is rotating. There you go. There you go. All right. So now our bright star down at the bottom, I hope you can see that, is drifting straight down. And that's the step that you're going to need to repeat for each star that you shoot. If you're working only in one small area of the sky, like there's a number of emission stars up there in the backbone of Cygnus that I like to shoot, you only have to make very tiny adjustments, because what you're doing is you're compensating basically for the effects of field rotation that's inherent in the alt-azimuth mount. So when you're shooting, say, directly in the west, as the star sets, you're not really going to have to rotate the camera because it's setting straight down. That aligns with one of the axes of the mount. All right, so after you have lined up your star, you've got it drifting straight down. Now is the time to focus on the spectrum. Slitless spectra do come to a focus at a slightly different location, focal plane wise, than the star. That effect is exacerbated if you are using a prism, I've found. The prism produces some astigmatism, and so the best focus of the spectrum is not when it's overall short. It's when the spectral lines are at their sharpest. So there's a few different tools that I use to focus a few different spectral lines. When I'm doing it low resolutions, then the hydrogen Balmer lines in an A05 star, that's something you've probably heard recommended before, is that you focus using the hydrogen Balmer lines because they're big, they're obvious, and you can see them even at low resolution. However, I did not know this at first, but hydrogen Balmer lines in A05 type stars, because they're on the main sequence, there's a very high pressure on their surfaces, and those lines are broadened. They are actually fuzzy. So as I kept increasing my resolution, I'd go to A05 type stars to focus, as I had been told to do, and I just wasn't happy. I was like, I'm not getting higher resolution, am I, despite my optimizations? Because those lines are naturally fuzzy. Even as you improve your resolution, they're going to stay fuzzy. So just be aware of that. Once you're at high resolution, you can use these telluric molecular bands. They're from the gases in Earth's atmosphere. This one right here is produced by water. These two dark ones flanking it on either side are O2. And they have some real fine lines in them. The water in particular, I find, is useful to focus at high resolution. I just focus until I've got the highest contrast between those lines there. And at any resolution, you can use narrow line emission sources. This one is P Cygni. And you do want to check and make sure it's not like one of those Wolf-Rayet stars, or I think some BE stars might have broad hydrogen alpha emission lines. So you want to make sure the lines aren't naturally broad, but I found that P Cygni is a pretty nice, reliable one to focus on. Okay, so after you have focused, now you position the star in the upper left corner of the field of view. I do that because I've aligned the star so that it's drifting down. That means that the farther towards the top of the screen the star is, the more exposure time I'll get in. And the farther towards the left, the more spectral range I'll get in, because I won't be chopping off this infrared on the right. And there we go. I just fast forwarded through the recording process, but I recorded that as a .ser video file. All right. Next up, I'm going to take that .ser video file, register, and stack it. I do that using a freeware program called Serial. That's S-I-R-I-L. I can put that name in the chat afterwards. Here I've opened Serial. Part of the reason to go with a .ser video file is that Serial can load that directly from the sequence pane. You do not have to convert it like FITS files. And also it's easier to keep track of the several hundred frames you'll get if they're in one file instead of a bunch of FITS. If you hit search sequences in Serial, it will look for your .ser files and automatically load the first one it finds. Then you draw a little box around the star. It's telling Serial where the star is in the image. Go to the registration tab, select one star registration, and follow star movement. I've found that Serial is much, much, much more accurate than things like Deep Sky Stacker for stacking spectra, because it can do this one star registration. It's searching the box for the star, and then wherever it finds the star, it will center the box for the next frame. So the box moves with the star down the frame. It's very fast since it's only searching a small amount of pixels. And there we go, registered all several hundred frames. Now for stacking, I usually do not use normalization. You also have the option here that you can use darks and flats. Personally, I don't always. It's probably a best practice, but because of, with the drift scanning method, your star, your target, is moving across the entire sensor. a lot of that repeatable noise that is removed by darks and flats is averaged out anyway, because you're averaging across the entire sensor. Hot pixels are never a problem with drift scanning. So that's just one of the benefits. It makes it a little bit easier for beginners. If, that's just one more thing to manage, removing hot pixels and using darks and flats, well, this is taken out of the equation. All right, so here's the spectrum. It's stacked. I'm going to pan over so that you can see the spectral features up close. This was Capella. All right, there we've got the sodium, or not the sodium doublet, the calcium doublet, magnesium triplet, and heading over towards the tellurics. Okay. Okay, so that's how you do it. You can now load that spectrum file into any software like RSpec, Visual Spec, whatever you would use to process a spectrum, and go as normal. When you do background subtraction, it's probably best, I'll show you. The background is uneven. Above the star, the background will be flat. That's a good place to select for background subtraction. However, see how it fades out and to black towards the bottom of the frame. That's because there is literally more exposure time at the top. That's the part that was always on the sensor throughout the entire drift scanning pass. So when you do background subtraction, make sure that you pick from an area that has the same amount of exposure as the spectrum, not down here on the gradient. Okay, so drift scanning method has quite a few pros, in my humble opinion, and I'm going to go over them real quick. First one, biggest one probably, is that it is low cost. It's accessible. Students can pretty easily swing this, and I think that there's opportunity for a lot of people to get into spectrography who have thought in the past that they just can't because they need too much stuff. They need a fancy tracking mount and an SCT and an L high res and a guide cam. You don't need any of that. All you need is a scope, grading, camera. That's it. And it's also simple, which I think helps make it good for beginners, because you have simple equipment. It's not difficult to set up. There's not a whole ton of stuff to learn the ins and outs of. And it's also a simple operation. That's not to say it's not time consuming. It's very manual, because for each star, you have to line it up in the upper left corner, rotate the camera, record the file. And then if you want more exposure time than a single pass across your camera, you repeat. So it is somewhat labor intensive that way, but the concepts are not hard. There's not really struggling with tech at all. So for a beginner, especially someone who wants to learn the sky, you're combining star hopping with just basically record and go operation. Because of how simple the equipment is, the setup is very fast, and so is the teardown, which can be important. I live in a somewhat tropical area, Houston, and down here, I don't know about everywhere else, but down here they have these trucks that go around and spray pesticides from the back to kill the mosquitoes. And more than once have I heard the whine of the truck approaching and just scooped up the telescope and laptop and run inside, because I don't want that stuff to get sprayed. So that's a pro in my mind. If I had to set up an equatorial mount, I just wouldn't be going out on nights where I thought the truck might come by, but I don't. So I'm able to get in Spectra on some nights, even when I'm not quite sure if I'm going to get interrupted. The magnitude limit, I've measured it to be around magnitude 9 with my 8-inch. Now, of course, that varies depending on what's your goal. If all you want to measure is the spectral energy distribution, well, you can tolerate more noise, you can go fainter. But for getting a spectrum with a reasonably low amount of noise, I found around magnitude 9, where I am in the city, is about accurate. That'll also change, of course, depending on your camera. If you're using a color camera, that'll be a bit lower because of the color filters cutting out some light. And I've found that I can get resolutions on nights of good seeing in excess of R1000 and recently in excess of R1500 on the brightest stars. Bright stars only because you do have to magnify the spectrum more to do that. So you're spreading out the light more and the faint stars kind of disappear when you do that. But on the brighter stars, let's say magnitude 2 and up, it is possible to push a star analyzer to very high resolution. Now let's talk about how to do that resolution optimization. So prisms, these 3.8 degree prisms are sold by the manufacturer of the star analyzer, Pan & Hawksley. They screw on right behind the star analyzer. And basically what they do is normally when you don't have a prism, the light's coming straight through the grating. The zero order light that creates the star image passes straight through, and the spectrum is produced heading off towards the side. So when you center the star in the scope, it will be centered in the image and the spectrum will head off towards the side. What the prism does is to take that light and to bend it just a little bit. This is not the kind of prism that would really create much of a spectrum on its own, but it can bend light and displace the image. And it's going to make the zero order image appear off to the side and the spectrum appear more or less centered. So that has the advantage of reducing an aberration, which is called spectral coma. And I'm going to be honest here. I've been doing research, but I still don't completely understand why spectral coma exists, but it does, and using a prism reduces it. The other optimization that you can make to your resolution, besides adding a prism to lower that spectral coma blur, is you can add spacers. This is actually the setup that I have been using recently. I know it's a ridiculous amount of spacers. It's actually as many spacers as I could fit in without contacting the secondary mirror of my 12-inch. And it looks ridiculous, but it gets me ridiculous results. So that's the important part, in my opinion. One of the reasons that using so many spacers works, well, there's two reasons. The first is that the more spacing you put between the grating and the sensor, I'm going to go back to this slide, the more spread out the spectrum will be, all right? It just has more time for the light to diverge. So if you had your camera sensor up here, you'd get a smaller spectrum than if you had your camera sensor way back here. Okay, that's what's going on. Also, the more spacers that you put, past a certain point, you're going to begin vignetting the light cone. That's bad for the #1 goal of spectrography, get as much light as you can into the spectrum. But it's good for resolution because you're vignetting away the outer image, the outer rings of the light cone. And that's where most of the coma is coming from. Spectral coma is like regular coma, and it will increase with the, it will decrease with the focal ratio of the scope. Higher focal ratio numbers means less spectral coma. Lower focal ratio numbers, more spectral coma. So an f4 scope, you're going to get a decent amount of spectral coma in your spectrum, but if you add enough spacers to vignette your scope so that it's at the equivalent of, say, f10, that sharpens up the image. So it's good for resolution that way. Now here, let's get to the juicy stuff. Here is an example I made. I shot the same target, P Cygni, back to back with way too many different configurations. Yes, I did all the alignments each time. And I made this comparison of the effects of a prism and spacing. On the left, we've got spectra taken without a prism. On the right, we've got spectrum taken with a prism. And the spacing increases from top to bottom. This is the lowest amount of spacing that I can get with my camera and its current nose piece, which is fairly long. So about 50 millimeters. And without a prism, so default, this is what you'd get without any resolution optimization. It's not super pretty. You've got the coma is creating this blur that kind of arcs away towards the red, right? And you can see here's the O2A band. It's almost arrowhead shaped, right? So that's not an excellent spectrum. But as we increase the spacing, the spectrum spreads out more. but it also is becoming sharper and sharper due to vignetting, removing that spectral coma, that finally at the end, once I went all the way up to 227 millimeter spacing, I've actually found using the grading without a prism to give sharper results than using it with a prism. I think that's because the prism introduces a curve to the spectral lines, like the smile in an ARAS spectrograph. So you can see here how the spectral lines are slightly curved, but without a prism, that effect is not introduced. You have straight spectral lines, and there's already enough vignetting at this spacing, at least for my telescope, that the spectral coma is almost null. You're approaching the situation of an objective grading, where the grading's not even in a converging beam at all. It's placed in front of the objective. That's the ultimate extreme of removing spectral coma. So the conclusion of all this is that I found that at low spacings, all the way up to moderately high spacings, it's best to use a prism because you will get that sharpening even though the spectral lines are slightly curved. Unfortunately, by the way, unlike, I believe, the smile in a ARAS spectrograph, the curve of the lines does change along the length of the spectrum. So it's not easily corrected with smile correction in programs like BASS. You can get a partial correction, but there's still always going to be some curve. So up to spacings of, let's say, 6 inches on my scope, that's, the prism gives better results. But then once you're up at really extreme spacings, you might want to experiment with removing the prism entirely and just allowing the vignetting to remove the spectral coma for you. And you might get results like that. Okay, so next, here's an aberration which you're probably going to notice if you start shooting spectra with decent resolution using a star analyzer. This is, these ripples that are going back and forth are thin film interference ripples. They're coming from the sensor substrate itself. The way I understand it is that there are some reflections within the silicon, which is a very, very, very thin layer. So you get this thin film interference effect from a very thin film, and that gives you ripples that get wider the thinner the film is. So at this at low resolution with a star analyzer, they are unfortunately quite large enough to interfere. You can see how they're shifting back and forth. That's because the angle of the incoming light changes as the spectrum moves across the sensor. Therefore, the wavelength at which the interference occurs changes at least slightly. So it's not, if it didn't do that, it might be more easily correctable because you could just describe the ripples and then subtract them from your spectra. Because it moves with wavelength, the effect of the ripples in your image will change depending on which part of the sensor your spectrum is from. So when you're doing drift scanning, if you allow it to drift all the way from the top of the sensor to the bottom, you'll average out the ripples to some degree. You might be able to get the rest by rigging up a flat of some sort using an incandescent light and a reflective wire maybe, and shoot a faux slit spectrum image. If you profile that and then add it to your IR curve, that should, in theory, remove the ripples. I haven't gotten a chance to try that yet. I just figured that out like 2 days ago. So just be aware, basically, that those ripples are there. They don't invalidate the data that's underneath, but you might want to ask, if you want to start contributing to AV spec, you probably will want to look into, is that going to affect your spectra detrimentally to the point where you can't submit them, in which case you're going to want to come up with a flat. And if you contact me, I will help you with any experience that I gain in the next week or so as I make my own flat to remove these. And I will make a post on my website once I have successfully subtracted the ripples that is a how-to, how you can subtract those ripples, so you can keep an eye on that. Okay, so now I've talked about how you do the method. I've talked about resolution optimization and the aberrations that you might see, such as these thin film interference ripples. Now I'm going to show you some pretty spectra in case you weren't convinced about the method yet. So here's an example. I recorded these at very high spacing, and technically they're not drift scanning because I did allow the spectra to drift over a long exposure instead of short exposure stacking, but who's counting? It makes pretty images, which is why I did it. Up here on the top, you've got Vega, got those nice, yummy, wide hydrogen Balmer lines, which, like I said, are naturally blurry. And then Deneb down here on the bottom. Vega and Deneb are almost the same spectral class, but their luminosity classes are different. Deneb is a supergiant, Vega's main sequence, and just look at the difference that makes. I find that to be absolutely fascinating. So Deneb is one of those stars that could be very good for focusing due to its narrow lines if you're using high resolution. Next up, we have P Cygni. This is one of my favorite stars ever to shoot. I took this spectrum just about a week ago, and yeah, it's beautiful to me. Look at that. I do believe that it is possible to capture a P Cygni line profile using a star analyzer. I think I'm close, in fact. Over here, there's a helium line to the right of hydrogen alpha, and I've got, in my latest spectra, I've got a little dimple there. It's not quite deep enough for me to call it, yes, I captured a P Cygni profile, at least not yet. But it's getting close. So I'm kind of just biding my time for a day with better seeing, you know. It's with all these cold fronts coming through lately, it's been a little tricky, but I think that it's possible to resolve a P Cygni profile. And man, what a great demonstration for someone who's learning spectrography. And honestly, how cool for anyone who's into spectrography. Okay, then there's this spectrum is just a small section in the visible region of a spectrum that I took of Arcturus. It's a colorization up there at the top. I wasn't using a color camera, but I overlaid a gradient on it in Photoshop. And this one, I was confirmed to reach a resolution of around 1000 or a little bit higher. That's enough to start splitting the sodium doublet and the magnesium triplet. Honestly, I think it looks better on the spectral strip up at the top. I did use a prism when I was taking this one, and I think in the end that ultimately lowered my resolution due to the curve. You can see this slant in the spectral lines. So in order to profile this spectrum, I just took a slice off of the very top where the spectral lines are more or less straight. That did mean that it got very noisy towards the ends. All right. Now, all the stars that I have been showing as examples so far are pretty darn bright. So a little proof that you can, in fact, shoot fainter stars with this. This one's RT Virginis. It's around 9th magnitude, if I remember. Took this one with an 8-inch. So I spent probably about 15 minutes exposure time on it. And it's one of my favorite spectra, honestly. I just love how absolutely crushed the visual region seems compared to the infrared. This star just takes right off. It's a type M8, so that's pretty far down there in terms of temperature. And one more example of a late type star. We've got Myra. I took this one just recently, and it's got some nice emission lines over here. Now this one, I also took as a single long exposure. Actually not a single long exposure. I took probably 8 or so long exposures, slant corrected them, and stacked them. However, I also took some drift scanning data that night. I was really just doing the long exposures because I wanted something pretty to hang on my wall behind me for this presentation. You can get results like this with drift scanning too. Okay, so to recap, drift scanning, it's simple. It uses really inexpensive stuff. So it should be accessible. And that's really why I'm pushing it, because I remember how I wanted for years to be shooting my own spectra, but I thought I was going to have to wait until I, go to college and get a degree and become a professional astronomer and find some observatory that'll take me in. And then I can maybe finally use one of their scopes to start shooting some spectra. And here I am a few years later, I figured out how I can do it without breaking the budget and without having to become a professional astronomer first. And I think there's probably a lot of other people out there who are in a boat like me, who want to shoot spectra, but they don't think they can. Either they don't think that they can afford what would be necessary to shoot nice spectra, or they think that they can't shoot high resolution enough spectra to be interesting with a star analyzer. I think I've seen that, because most of the star analyzer spectra that you see are taken with low spacings. Great for limiting magnitude. You can get some faint stuff that way. But I don't think that people realize that you actually can get resolutions that are comparable to low resolution slit spectrographs using a star analyzer. So that's possible. I hope I've busted that myth today, and also busted the myth that you need tracking, because you don't. And I would like to encourage anyone out there, if you are a beginner and you want to shoot spectra, you're not sure where to start, this is a good place. This is a good place to start. If you are a teacher, maybe you have an L-high-res spectrograph set up already and it's real sweet, and so you're not going to be using this method. That's totally understandable. But one day you might encounter someone who says, oh, hey, I saw that cool spectrum you took. I want to do something like that. And then their eyes glaze over when you start telling them about how they can do it like you, with the tracking mount, the slit spectrograph, the guide cam. Maybe you can make the suggestion, instead of just buy a DSLR, buy a star analyzer, put them together, get a lump shaped spectrum. Maybe you can put this out there as a middle ground. If you want to start seeing some real high resolution spectral features, but you don't need to go all the way to the very, 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 very high resolution of an L-high-res. Here's a middle ground, And for anyone out there who's curious about this, I have a website in which I have written a very detailed step-by-step how-to guide on how to do the drift scanning method. And I'm going to keep updating it as I learn more and learn about, for example, how to make the flats to cancel out the interference ripples. All of that's going to be being added to this website. The website is called tiedyeastronomer.com, which is the latter part of my email address, which I'm now going to beg you to contact me on, because I don't know if you can tell, but I love teaching. This is what I live for. And if I can help you in any way to get started with the drift scanning method, or just if you have any questions about spectrography in general, shoot me an email. I'll do my best to answer. If I can't answer, I do know a whole lot of people who might be able to answer that I can put you in contact with. So it can't hurt. Thank you for your time.
Thank you very much, Lauren. That was, as always, excellent.
And Ken, may I mention something?
Pardon?
Somebody was asking for mentors. Lauren can be an excellent mentor for those who are interested in this type of observation. And she is one of the AAVSO ambassadors. So she could, and she's a very gifted teacher, as you can tell. So feel free to contact her. Or contact us to bring you in touch with her. Feel free to actually build this kind of connection, because she's learned the really hard way. So she's learned by doing, and she knows her stuff. That's all I have to say. Thank you.
I second everything Stella said. And one of the nice things about Lauren is she's so creative and so original in how she approaches things. And she's also very willing to share, which I think is kind of a hallmark of the spectroscopy community. People in this community are willing to share and help each other out, and that's excellent. Now, we do have time for a couple of questions here. James said, great presentation. Do you rotate the camera in different directions to align the drift vertically? What determines if you have to turn the camera left or right? Does it matter which side of the meridian you are observing?
Okay, great question. Yes, it does matter which side of the meridian. I'm going to go back to the video and use it as a visual aid here. That would be this one. Okay, so the angle here, this red angle that the star is tracing out with respect to vertical on the camera sensor, that is the angle that you need to rotate the camera. So you would take a point on the camera, which is straight down, and rotate it towards the right. In this case, because the star and spectrum were drifting towards the right, you'd rotate the camera to the right. If the star and spectrum were drifting towards the left, you'd rotate the camera to the left. Okay, that's my answer.
Okay, thank you. The next question is from Patrick. He said, Lauren, in your workflow, you speak of focusing, but how did you determine optimum exposure time? Perhaps because you were recording video files, this is not an issue.
For exposure time, I do the longest exposure that I can get away with without either saturating the spectrum or trailing the spectrum over any background objects. That usually comes out to be about 1 second long because that's the point in which I normally start encountering interference from trailing over background stars. So that's where I max out for anything that's not so bright that it would saturate the sensor. If I'm shooting Vega or something, then I usually limit the exposure to around 100 to 200 milliseconds so that it won't saturate. Basically, I just watch the histogram to make sure.
Thank you. Paul wants to know, have you compared cameras that are 12-bit versus 14-bit?
I have not compared them rigorously. I do have one of each, I believe. I have the ASI 178mm, which is 14-bit ADC, I'm pretty sure. And my latest camera is 12-bit ADC. It's a 183mm Pro. I have not really noticed a difference. They both take great spectra, so.
Okay. Mike wants to know if there are any issues or trade-offs using a 16-inch 4.5 Dob with this technique.
That should be a wonderful scope for this technique. You've got a lot of aperture on your side.
All right, and then one more question. James wants to know, what do you think about fast telescopes? I have a 5.5-inch f3.64 Schmidt Newtonian.
Interesting question. I have a friend who's been doing some really great high resolution work with an f4 Schmidt Newtonian. I think that fast telescopes are, if you're shooting at a low dispersion, you're going to get a lot of spectral coma. But I don't think that they're really limited if you're okay with increasing the spacing to the point where you're vignetting away some of that spectral coma. You are going to be losing light by doing that. And it was a 5.5 inch, I think. So you'll have to consider to what diameter you are vignetting it to. But I'd say go for it. The Schmidt Newtonian design is already cutting down on zero order coma, at least. And just, I know people who are doing great work with F4, so give it a shot.
Okay, thank you very much, Lauren. And just in closing here with Lauren's talk, I would really encourage everyone to visit tiedyeastronomer.com because it's really an excellent website with a lot of very fascinating information on it. So when you have a chance, take a look at it. It's excellent and super well done. Thank you, Lauren.
Thanks, Ken.
Okay, next up, we have a talk on planetary nebula by two great spectroscopists, Olivier Garde and Pascal Ledoux. Basically, between the two of them, they seem to almost know everything there is to know about spectroscopy. They're both great spectroscopists and really impressive. And so with that, they're going to give us a presentation today about planetary nebula, which is kind of a unique area that not a lot of people are doing, I don't think, although they've put together a very interesting team in France of people who are observing and classifying planetary nebulas. So with that, I'll turn it over to the two of them.
Okay, thank you, Ken, for this introduction. And I would like to thank you again, the AAVSO, for inviting us to present our work. With Pascal, we will present you a Pro-M program for confirming planetary nebula candidate with spectroscopy. So first, I would like to apologize for my English, and I hope you will understand me, of course. So I am Olivier Garde, a French amateur, and I have been doing a spectroscopy since the year 2000. I live in southeast of France, near the Alps, close to Switzerland, and I have my own observatory in the countryside. So I share my screen now. Okay. So our presentation is for confirmation of planetary nebula candidate with spectroscopy. I would like to start with a short history of this Pro-M collaboration. This collaboration was born in 2003 during a CNRS meeting in France with amateur and professional, with Professor Agnès Hecker. She's an astrophysicist specialized in planetary nebula physics. And in 2008, the first new PN discovery was made by a French amateur, Nicolas Auter. And some years ago, in 2011, Pascal Ledoux discovered his first PN on his own image. In 2012, Christian Brill takes the first spectrum of a PN candidate. And in 2014, the PN candidate list was created. Professor Agnès Hecker retired in 2017, and now it's Professor Quentin Parker from the Hong Kong University take over the project. So at this day, there are more than 400 PN candidates have been discovered, but there are only 32 who have been confirmed with spectroscopy. So it's very less, and we have a great job to do. In 2014, we have a meeting in Paris. Here is a picture taken during the first meeting about this collaboration with observer, discoverer, the amateur in spectroscopy, and Agnès Hecker at the French Institute of Astrophysics in Paris. So we take a day to discuss about how to confirm a planetary candidate nebula with a spectroscopy. So what are the objects we are seeking to confirm? This is some well-known example I show you here with M57, with helix or other target showing a ring or an ellipse or a circle like this new nebula, bubble nebula discovered by Dave Jurasik and validated as a PN by Agnès Hecker when he discovered it. So what is a planetary nebula? A planetary nebula forms when a dying star casts off their outer layer of gas. In the center of the PN, you have a very hot star around 33,000 Kelvin who ionized the shell of gas ejected by it. This gas show emission line in spectroscopy, mainly the forbidden oxygen line and the H-alpha line. Now, Pascal will now tell you about the PN candidates and how they were discovered. So, Pascal.
Yes, thank you, Olivier. Hello from Brittany. I am an amateur like Olivier Garde. I manage 2 tables of PN candidates discovered by amateurs. I discovered some PN myself, but now I mainly perform spectra of PN candidates to confirm their nature. As an amateur, you can find a PN candidate in 2 different ways. The most productive way is to explore images of professional surveys at different wavelengths. For the second way, you have to use an astronomical setup to take image of the sky with the O3 and H-alpha filters. Obviously, it is possible to use these 2 methods together. The goal is to identify an isolated signal with a PN morphology. You can change. Thank you. To discover PN candidates, we use 2SIS2 high-files and DKPS images in the visible. We also use mid-infrared wise images because some PN send visible dust of these wavelengths. With Aladdin tool from the Strasbourg Data Center, it is very easy to look at a mosaic of several professional surveys images. It is possible to browse and inspect images for suspicious signals and compare them at different wavelengths by using plane overlay with transparency. You can change. Thank you. Like for our own images, we can make some basic operations with professional images, like a subsection of cotinium to contrast a faint signal. We can make image color composite to revolve a typical color of PN. In the right, we can see 2 composite images built from wise bands. In the top, the candidate in the middle has a yellow color when we use the band 4, 3, and 2 of wise. When we use the band 3, 2, and 1 to build the composite image, the color of the candidate is red. These colors are good indicator of true PN. We are also looking for the central star candidate with high resolution images, like those from Penstar or DKPS surveys. The central star generally looks like a small blue star in the center of the nebulous disk. We seek also information of the central star from Gaia data. You change. Thank you. In this slide, there are some professional images of PN candidates from DKPS and Penstar's images. These candidates show nice nebulous PN disk with a central star candidate in the middle. You change, please. We can see in the slide 10 some discoveries of the German Marcel Dössler and the Norwegian Garde. It's a very good candidate. To discover a PN with your own setup, you don't need a big telescope, but you have to use optics with a small FD ratio with an efficient camera with a large sensor. The goal is to capture a very weak signal. You should use Neuroband filters centering in the O3 and H-alpha bands. you have to add many images to get a very long exposure time. You can see in this slide some PN candidates image discovered by amateurs. An example, OU6 PN discovered by Nicolas Hutter. See the total exposure time, very long time, and the particular color of this PN in the ASHO image. Another example, the LDU13 PN discovered from an H-alpha image. If the detected signal is confirmed, you must ensure that it is not already referenced in CIDBAD, Vizier, HPN database, or another list from a scientific past paper. The criteria for selecting an object are isolate and nebulous signal, morphology, round, disk, round, bipolar, very weak signal from S2 filter and DSS2 infrared images, flashing colorimeter from SDSS, DKPS, PenStar, or SHO image. We also look at the signal in mid-infrared image from WISE. We are looking for a contrasted spot from W3 and W4 bands. And we look at if a central star is present in PenStar or DKPS images. These criteria were told us by Anya Saker and mentioned in Jacobi paper. Two lists of PN candidates discovered by amateur are managed. At the beginning, there were only French discoveries, but now there are many discoveries by amateurs of other countries, from USA, India, China, Norway. There are more 700 objects in the list 1 and more 130 objects in the list 2 in 2020. The selected objects are classified as possible PN, likely PN, or true PN in the list 1. Objects of unknown nature are classified in the list 2. Each object is referenced with the first letter of the discoverer, followed by a number. These lists are regularly sent to professionals, such as the Strasbourg Observatory or the University of Hong Kong. You can find them in Vizier and in the HPN database. In this slide, we can see the link of our list in the Strasbourg Data Center with Vizier. For maximum transparency, you can find all PN candidates from our list on the website planetarynebulae.net. Each object has a datasheet with image and a spectrum if it was made. You can find in PNNet all the PN spectra that were made by amateurs. We will see that later in this presentation. To confirm the nature of an object, you need a spectrum, but images taken with a very long exposure time or with a professional telescope provide many details about a PN candidate. It is possible to view the different regions of the object. This image can help center the sleep of the spectra, for example. In this slide, some images taken with a very long exposure time by amateur astronomers. Another image taken with very long exposure time by amateur astronomers too. Here we see detailed images of the object, unlike what was detected on the DSS2 images. Some images of PN candidates taken with a professional telescope. Here we see typical image of PN. And now, I leave the place to Olivier.
So now I will now explain how we realize and use the result of a PN candidate spectra. First, to take a spectrum, you of course put the target into the slit, but sometimes we don't see the target too weak to be seen on the auto-guiding field sensor with few second exposure. Then we process the raw spectrum to obtain a 1D spectrum, like you can see on this picture. Here is for M57, so it's very bright PN. And you have the graph. There is a classical PN spectrum on the graph with many emission lines which are identified on the graph. In 2017, with a group of friends, we create a PNST, Planetary Nebula Spectra Tracker. Our goal is to confirm PN candidates with spectroscopy. And we have created an association in 2019 to perform spectra from the southern hemisphere with our association. His name is Two-Spot. Two-Spot means Southern Spectroscopic Project Observatory Team. I will explain later where we will install our future setup. We, of course, try to confirm PN with our respective equipment from home, but each year we do some one or more mission in observatory with telescope of wider diameter. In French Alps at Saint-Véran Observatory, above 3,000 meter altitude, we have two telescopes of 500 millimeter in diameter. At OHP, Haute-Provence Observatory, during the annual spectral party, and also at Cannes Observatory with a 1 meter telescope near the French Riviera. We use a very sensitive spectroscope with a good efficiency, like the ALPI 600 or LESA spectroscope, or maybe the new UVEX spectroscope. We tried to do some target with it. And for the optical instruments, we use several telescopes of different diameter, from 200 millimeter in diameter and up to 1 meter. So we put the target into the slit. You can see on the screen the slit in white. This is a negative image. And we do auto-guiding on the star close to the target in the same field of the auto-guiding sensor. Why? Because sometimes the target, we don't see the target in the slit, so we can't do auto-guiding on this target. We use a DSS sky map and Aladdin software to put the target very precisely into the slit. It's very important to have a good precision to not lose light from this very weak target. On this picture, you can see the slit, the target on the sky, DSS sky map, superimposed on the auto-guider image. Here is a sample of a very faint target. We don't see it into the, the target. You see a red cross on the screen. This is the target, but we don't see it. But we know that it was at the good place. So here is the acquisition procedure for each target. We took several single exposure of the target. Typically, we take 4 exposure of 900 seconds each, or maybe 6 of 1,200 second total exposure each. After each target, we take a calibration lamp. The argon neon lamps included in the LESA spectrograph. We take also some flat, around 40, with a tungsten halogen lamp included in the calibration module. We take a spectrum of a reference star close to the target. you can use the spreadsheet made by Francois Teyssier, very useful. You have the link to download the spreadsheet here. And of course, we take bias and dark depending on the time exposure. So this is a raw spectrum of a single exposure of 900 seconds. You see the spectrum of the target, the green rectangle. You have also other spectra of the star already present in the slit on the atmospheric and interstellar line. During the process, we must subtract the background sky from the target spectrum in order to remove the atmospheric and interstellar line and the light pollution. Like other targets, we have to take a reference star close to the target for the instrumental response. Here is some results. This is the ARA24 PN candidate. You can see H alpha on oxygen line in emission. And the two lines of oxygen have the good ratio, because you have to have a ratio between the two lines present here on the graph. You have O3 here and O3 here, and you have the ratio between these two lines. If the ratio is good, this is confirmed like PN. So this target is a PN. And now, if you go, you check this target in Symbad, you will find that now it's a planetary nebula confirmed with our spectrum. So here is some other targets. Some are planetary nebula, some not. All these targets are under study by Professor Quentin Parker in Hong Kong University. So the two up spectra is PN confirmed, and the two below spectra are not PN. And sometimes we have a strange result like this one. In this case, we send our spectrum to various astrophysicists like Professor Steve Shaw, and I let you read his answer. We send the spectrum the night, and we have the answer at the beginning of the day after. So it's very interesting to have a comment of a spectrum when we are in mission to take spectra for PN confirmation. Another one strange object. This is HU6. You can see a Balmer line are present, and you can see a small emission here. This is H alpha line. Is very small emission, hydrogen in emission here. So, of course, we don't know what kind of object it is. So we send this spectrum to Professor Steve Shaw, and we have this comment. So maybe it's a dwarf nova. And another strange object, it's APP1. So you can see some emission line like H alpha, but if you look closer, you can see that H alpha line is shift on the right of the spectrum. All the emission lines are not in the right place. So what it means? Here is a comparison with the target within our galaxy. It's KN66 on APP1. And you notice that the lines are well shifted toward the red. So we calculate the redshift Z of this target using the emission line and the velocity of this galaxy and the distance thanks to the Hubble constant. at this time, we have discovered 4 new galaxies that are not listed in the catalogs, and we have written an article of this discovery that you can download on the link given in this slide. So at this day, only 32 candidates were confirmed as a PN. We have a lot of work because there are 400 other PN to confirm. So if you want to embark to this adventure, Pascal will now describe the website we have to set up.
Okay. You can find in a PNNet all the spectra of PN candidates made by amateur astronomers. A page is dedicated to it. The targets come from our list, but also from the ARAS PN database. Many PN candidates, including ours, don't have a spectrum in the ARAS PN database. In PNNet, you can view amateur spectra with their metadata sheet. You can see quickly the emission line detected for each object. Many amateur spectra have been used to change the status of PN candidate in ARAS, but some poor quality spectra require additional observations. So you feel free to try them again. Olivier, you can.
Okay. You can have many information about PN confirmation or PN candidates in the French magazine L'Astronomie. Sorry, this is in French only. But there are many issues of this magazine who talk about planetary nebula and confirmation. Several articles written by Pascal, like in this issue of March 2019, with an article of 6 pages. Here is a poster presented at the SF2A Congress in 2018 during the annual meeting of the French Astrophysical Society. And at this time, this is why we have created an associative structure. Sorry, I missed one slide. Look at this slide. You have all the galactic sky of our galaxy. And the many targets are in the southern hemisphere. You see on this map the red dots of target confirmed in the northern hemisphere, few in the southeast, but very few targets in the southern. So there are a lot of job to do in the southern hemisphere. So that's why we created an associative structure recognized for of general interest with a scientific vocation, 2 spots for Southern Spectroscopic Project Observatory team. We are 5 amateurs who join together to pool financial resources to install a spectroscope setup in Chile in the Atacama Desert, where there are more than 320 nights of clear sky each year, seeing less than 1 arc second. So very good condition to take spectrum. Our association can receive donation from everyone, and we hope to be able to install the equipment in early 2021. It all depends on the COVID virus evolution. This picture shows the place where we are going to install our spectroscope. So thank you. That's the end. And thank you for your attention. And feel free to ask any question.
Thank you, both of you, Olivier and Pascal. That was an extremely interesting presentation. And it's nice to see such a unique observing program. It's also really good to see, just as an observation, the level of professional amateur collaboration that's going on with this project. That's excellent. And I'm really impressed with what a good team you've built to do planetary nebula confirmation. We do have some questions here. The first one is, Olivier, what software are you using for guiding?
Alors, for my setup, I use MaximDL software, but Pascal use Prism software to do auto guiding. It's depend in our group. We are 5, and so each one of us use different software, mainly Prism and MaximDL.
Okay, thank you. Yes, I've noticed that a lot of people in France seem to use Prism. I don't think it's used as much in the United States, but maybe it is, and I'm just not aware of it. Keith wants to know, do you prefer to avoid the central star if it is present?
It's difficult to catch the central star with this kind of target because the target is very, very, very faint, more than magnitude 17. And we have all, why we have a spectrum? Because we have all the emission line present in the circle of the planetary nebula, but not of the central star. It's not possible.
Okay. Andre wants to know how to make a good interstellar correction for a planetary nebula.
We are lucky because in low resolution spectra with LISA or ALP 600, we catch. I come back to the slide before. Here, we have, you see on the green rectangle, you see the banning area where we have the information of the PN. And you have also up and down of this green rectangle, you have 2 areas of the background sky. So it's not difficult to subtract this background sky to our spectrum to eliminate all line, interstellar line, pollution line, atmospheric line. It's doing, we do with, during the process with ISIS or Demetra.
Okay. Stephen would like to know, is the placement of the slit across the center of the planetary nebula or the gas ring around the planetary nebula?
You know, the target, it's very, very faint and it's very, very small. Sometime we have, just voilà, look at this planetary nebula. You see, it's a little dot. It's a dot like a star finally. So we just put the target into the slit. You see there we can't see a ring. We only see a dot. So it's not difficult to put the dot inside the slit. Some planetary nebula are a real area. So we put the slit on the area, the main area where more luminous to have more chance to have a spectrum.
Okay, thank you. I'm curious about, I have a question myself. I'm curious about your team of people. First off, how many people are on your team?
We have different team, but the main team, we are 5. With Pascal, with Stéphane Charbonnel, with Lionel Mulato, with Thomas Petit. But we have also another people who work with us to take spectra of candidates. It depends, but maybe Pascal, you have something to say?
To take a spectra of PN, I think there are 10 of people, I think, yes.
Okay, and do you have meetings ever together, or do you just do everything sort of remotely with email and phone calls?
We have the website, like this website. Yes, this one. On this website, we have put many information about candidates, and sometimes we put a special message to say they have a priority to take spectra from this kind of target. We have new target, so all information are on this website. But sometimes we can discuss by Zoom or by mail, it depends.
Okay, all right. Well, I think that those are the questions we had, and it was a very interesting presentation. Thank you very much, both of you.
Thank you, Ken.
Thank you.
Mm-hmm. Okay, I believe at this point, it's time for a break. So I'm going to ask Lindsay to jump in here and take charge.
Yep, so shortly at 2:10, we're going to be convening back. Originally, we did not have a break scheduled, but Ken is certainly right. We are ended a bit early for our next round of presenters. So to give them some time to get their presentation together, you're welcome to take about a 5-6 minute break now, and then we're going to reconvene at 2:10. Or 2:10, sorry, Eastern time. It's going to be, let's see,
Lindsay, actually,
1910 UT time.
It'd be 1920, wouldn't it?
Nope, we're convening at 1910. Vincent Suk and Andres Jordan are going to be giving a short presentation at 2:10.
Oh, okay. All right, great. So we'll be back at 2:10. And then after their presentation, we'll have David Boyd talking about using Python to analyze spectra in the ARAS database. And then after that, we'll have Francois Teyssier with a presentation on symbiotic stars. So lots of good stuff still to come. Thank you.
All right, we'll see you in 5 minutes for some telescope hosting time.
Lindsay, it's Ken. Are we ready for our next presentation?
Yep, pulling it up.
I'm Vincent, so I'm CEO at Obstex. I'm in charge of the organization and what's happening at the observatory. So Obstex started in 2012. We started as investigators of the university, and we had telescope in Las Campanas. And the idea was to make an alternative to amateur astronomers and professionals for having a site for robotic telescope. The observatory at South started at very little, a single building at the beginning with only 2 amateur astronomers, 2 small telescopes. And now it grew up to 37 telescopes actually running on site, 40 by next month. And we are building a new building for 11 telescope, which is almost full. And we'll start another building for 11 more telescope. The idea of Obstex for the next few years is really push on one side on amateur astronomers for having the best service for amateur astronomers and astrophotography and collaborative science. And this real high-end alternative will give the best service for amateur astronomers.
I'm Samuel Robert. I am the CDO of Obstex, mostly concerned about the development of new technologies in the observatory, and also I take care about the systems that make possible this observatory to work remotely. The main specs of this observatory are a very high bandwidth of internet. We have 3 independent connections. One is a 100 megabyte symmetric fiber link, which is the same one that is gonna feed the new LSST project in Cerro Bachón. Also, we have a second radar link, which is about 70 megabyte symmetric bandwidth. So that is powered by a solar plant. So we have more than 20 kilowatts in solar panels generation. This is a world-class observatory. In terms of clear nights a year, we have in average more than 300 clear nights. Last year, 2018, we had 320 clear nights a year. The average seeing is around 1 arcsecond, mostly below it, depending on the season of the year. And we have normally low humidity. There's not much wind during the night, so it's a very good site for a telescope to up 1 meter.
Hi, I'm Jonathan. I live on the site. I'm here to keep an eye on your setup, to collimate, to installing or cleaning your equipment, to be sure all is fine.
Hi, I'm Rodrigo. I am an automation engineer. I take care of hardware development of the observatory. I work in Santiago, but periodically I go to the observatory to perform the upgrades and maintenance in the observatory system. This is my job.
Hi, I'm Abner. I'm finishing my PhD in astronomical instrumentation and recently joined to Obstex team as manager operation to oversee all the support and administration. I'm in charge of manage the people that works with us. That includes technician support and the guards.
The observatory is not only growing in terms of number of telescopes and buildings, but we are also growing in terms of activity. We are doing a new workshop, new dorms for the people working on site. And here behind me, we are building a new house, mostly for amateur astronomers who want to come here to stay on site, either to install their equipment or just for stargazing and having a large Dobsonian telescope to take the best advantage, the best sites in the world for stargazing and real visual observations.
So there you have it. That is our sponsor, OBSTech. They've been really wonderful to communicate with over the past couple months. And you can also go to their website. I'm going to pull it up here. And so this is their website if you're interested in their telescope hosting services. As you can see, it's they have a lot of perks to offer any client of theirs. And we are really grateful for their contribution to the AAVSO, because as a nonprofit, our sponsors, our contributors are really, really important to us functioning. So a huge thanks to them and to Vincent Suk and Andres Jordan.
Okay, yes, thank you very much to both of them and to OBSTech. We appreciate the support greatly. Our next presentation today is by David Boyd. David is a former president of the British Astronomical Association and an experienced spectroscopist. And he's going to be talking today about using Python to analyze spectra in the ARAS database. There's been a lot of interest lately in the amateur community on using Python to do various tasks. And we have two presentations this year that relate to Python, one by David and another by David Whalen, talking about using Python for data reduction. So in any case, I think that this is going to be a good presentation. I'm looking forward to it very much. And with that, I will welcome David Boyd.
Thank you, Ken. I will try and share my screen now. Oops. Okay. Good afternoon, good evening, good night, wherever you are in the world. I'm going to be talking to you today about using Python to analyze spectra in the ARAS database. There are three themes to the talk, really. The first is that small telescope scientists are collecting lots of high quality spectra now, which have got potential scientific interest. We need to promote the usefulness of these spectra if we're going to encourage their use by the professional community, because they won't necessarily find their way to these spectra without a little bit of guidance. And I would argue that Python can be a great help to us to achieve this. So the ARAS spectral database, ARAS stands for an astronomical ring for access to spectroscopy. It's an initiative started in France to promote amateur spectroscopy and also encourage pro-am collaboration. This database was originally developed and is now maintained by Francois Teyssier, who you will be hearing about shortly, talking about symbiotic binaries. It mainly collects spectra of symbiotic binaries, but also any nova and even cataclysmic variables, which are bright enough to be recorded by amateur spectra. All spectra are submitted as FITS files, conforming to the BES FIT specification that you've heard about already today, defined by the BESS project. And it's really the specification of FITS, which is used by most amateur spectroscopic databases now around the world. The main features of the ARAS activity are
that we can respond quickly to alerts, either because one of our observers finds something interesting, or there's an ATEL comes out, or there's a personal contact from a professional astronomer. And we can start taking spectra, possibly before professional telescopes can actually be activated to follow it. We can do long-term monitoring, and we can follow objects for, again, longer than it might be possible in professional observatories. And we have potential with many observers around the world to obtain a high cadence of observation. And we actively are trying to collaborate with professionals, as you'll see later in the talk. And there's the link at the bottom of where you could find the database on the internet. Here are some examples, just 4 examples that highlight some of the diversity of the database. Top left there is a spectrum from Jacques Michelet in France about AG draw, symbiotic binary, obtained with ELISA, a medium resolution spectrograph. Top right is a spectrum from Tim Lester in Canada, obtained with a homemade E-shell of V694 MON, a very interesting symbiotic binary with a colliding jet, a collimated jet. And at the lower left, spectrum of cataclysmic variable that's been exciting quite a lot of interest recently. That one's obtained with an L-high-res spectrograph using a lower resolution grating. And at bottom right, a spectrum of a recurrent symbiotic nova in Sagittarius from Paul Lucas in Australia, again, obtained with an ALPI. I should have mentioned that Paolo Berardi is in Italy. So we have pretty well global coverage of people submitting to the database, but also a wide range of resolutions available, which are good for different aspects of studying spectra. If you want to submit a spectrum to the database, we're expecting that you will process your spectra by applying the normal sort of corrections, offsets, darks, and flats, doing wavelength calibration, probably with the built-in calibration lamp in your spectrograph, that you will make corrections for instrumental and atmospheric response or losses with a response correction using a suitable reference star. If you're working at high resolution, it may be better to rectify your spectrum rather than trying to do a response correction. But spectra generally should be compliant with the BES fit spec and have a spectral resolution above about 500. We set that limit because the sort of science that we're trying to get out of these spectra is really only achievable when you get spectra above that sort of resolution. There is a simple validation check we make prior to adding spectra to the database, but it really is the observer's responsibility to verify the quality of the spectra. So that we're expecting the observers to do the spectrum carefully and process the spectrum carefully in the way I've described. We do provide feedback to observers, and we're certainly keen to help them develop their observing and processing skills and mentor them to the point where they're producing reliable spectra in the database. Almost all spectra in the database are exoatmospheric spectra. That means they're corrected to a point outside the Earth's atmosphere, as though they've been taken with a perfect space telescope. And they're relative flux spectra, which means that the spectrum is consistent across the whole wavelength range in flux, but it's not calibrated in absolute flux. And that's something that we have to then tackle in the database. Just some of the issues encountered. These are not exhaustive, but it gives you an idea of the range of sort of issues you come across when you're trying to work with spectra in a database like that. We've very occasionally even find the wrong object has been observed. Not very often, but it has happened. Software for processing spectra is complicated, and particularly with new users, there are mistakes that sometimes get made, and we try and hold people's hand through the learning curve on new software. Low signal to noise is not an uncommon problem, sometimes due to poor guiding or just poor scope focus. Insufficient exposure might be common because of interruptions of observing sessions, and people don't get as much data as they'd hoped. Poor spectrograph focus, certainly with some spectrographs which are subject to temperature changes and flexure, is something that has to be watched closely. We certainly encourage people to pay attention to that. It makes certainly a significant difference to the quality of a spectrum. Wavelength calibration is important. People can misidentify lines in the spectrum less so as you get more familiar, but some of these calibration spectra are complex, and it's not always straightforward when you're starting to know which line is which. Poor response correction is due to things like people choosing an inappropriate reference star, maybe a variable reference star, or one with a really rather complex spectrum, or choosing a star at a different air mass from the target star. These can lead to a poor response correction, which affects the shape of the continuum. And that makes it difficult to then use that in scientific analysis later. If you find a spectrum with an emission line that nobody has ever seen before, the chances are it's not a new element, it's probably a cosmic ray or a hot pixel. And the best way to investigate that is to have a look at your sub-exposures, and you'll probably find one of them has the culprit event there, and you maybe just drop that sub-exposure. And even with E-shell spectra, there are problems. They're complex operation joining the various orders, and that can sometimes lead to a problem in a spectrum. And the other problem, not uncommon, arises from the FITS header, because different software have adopted different keyword names for the same variable. FIT stands for Flexible Transfer Protocol, and I think the word flexible still comes through into the way it's used in many cases. So there are some problems that we come across in that area. Gradually, we're trying to iron these out. The Eruptive Stars newsletter, which is really a part of the ARAS initiative, it's a quarterly publication, initially started by Francois. Woody Sims and I are now helping him edit it on a quarterly basis. Its purpose is to report recent submissions to the database and provide information about the particularly interesting behavior that we think some of the stars are showing in that quarter. Its aims are to encourage observers by giving them a shop window to show the results that they're collecting, and encourage them through that channel. To promote their data to a wider community, particularly hoping that professionals will pick these up, and to actively engage with professionals. And for that reason, it is now indexed on ADS, which means that if you search for some of these stars, you will pick up the references to the newsletter. And there's a link there along the bottom. But if you just Google for Eruptive Stars newsletter, I think you will probably pick it up. Now, promoting the database, as I've said, is an important task, really, to ensure that the spectra are used. We've got 10 years of data on some of these objects, and it's a valuable resource if someone is trying to study time-dependent behavior of those objects. The density of coverage is often greater than you will find in professional observatories. So in that reason, it's a valuable resource. But availability and quality really do need to be promoted. And the newsletter is a channel for that, but we need to do more than that. We need to have tools to help us present the data effectively. And we're taking care not to interpret the data. I'm trying to distinguish clearly between just presenting the data and make it visible, but we leave the interpretation to those who know better about how to do that. We decided that we needed custom tools to do this. There are lots of software available for analyzing spectra, but less for the sort of things that I'm going to be showing you here. Francois did a lot of that initially in MATLAB. We're now starting increasingly to use Python for doing that. So why choose Python? Well, it's really the development environment of choice for astronomical software these days. It's widely used in the professional world. There are conferences, hack weeks, means of getting grad students up to speed in it. The AstroPy community project is a great range, offers a great range of software, and there are various packages affiliated to that within that family. And it really means that most of the core functionality you will need in processing spectra is available. There are lots of examples of code available online, and it's certainly in the last year, I've picked the language up simply by Googling, how do you do this in Python? And you'll find ways to do it, and you gradually bootstrap yourself up. I use the Spider interactive environment. Other environments are available depending on what takes your fancy. Very simple Python script. One of the first things I worked on was just something that will read a FITS file of a spectrum print you out the header. You can see all of the keywords on the right-hand side and their values, and that immediately gives you access to information like what the object is, what software was used to analyze it, what sort of resolution it is, and that program will print out a spectrum just to let you see what the lower left shows you an example of one of the symbiotic star spectrum from that software. That's first level of getting started. But then we've had to write more Python to do things like download and read all the spectrum in the database from a particular star, because in the database, some stars have got several hundred spectra, and we want to be able to analyze those as a block of data. So we need to download and read the spectra. That reveals many of these FITS-related issues I've mentioned before, things like Julian dates, which you want to use aren't there. You have to calculate them. Some keywords, some quantities, such as spectral resolution, there are at least half a dozen keywords that get used by different packages. So you have to figure out which one is the one you want to be using. These have to be resolved when you're reading the spectrum, and we do apply corrections, but and we request often improvements back to the software developers to try and ensure a degree of consistency, at least in the implementation of the FITS system. BESS is still the core, but there are still a number of variants which are being in current use that we have to deal with. And a closer examination will always reveal some problems that aren't picked up during the initial validation check. These are things like poor response correction that I've mentioned, which could cause a problem downstream. So we'll flag these up and bear them in mind when it comes to analyzing the spectra further on. A simple thing that you could do with Python, which is useful, is you can use Python to read the FITS parameter headings in the FITS parameters, compute the altitude and air mass at which either the reference star or the target star were obtained. There are nice functions in AstroPy that will make that a relatively simple job. It's only a few lines of code, and it can then be very useful to diagnose a problem. The simple example there run on one of my spectrum, down at the lower right, you can see it gives you the initial and final air mass of the target and the initial final air mass of the reference star, and that lets you see that clearly these were consistent, and therefore the response correction based on that reference star should be a reasonable one to use for this particular spectrum. Now, interpreting spectra, most spectra in the database are, as I've said, relative flux spectra. These show the main qualitative features of a spectrum. They show the main emission lines. They will show if it's an M-type star, for example, is the giant that receives prominent titanium oxide absorption bands, and they'll show the general shape of the continuum profile. You can calculate equivalent widths of spectral lines from it, but they give you limited quantitative information for comparing spectra. If you want to see how a particular object is evolving over time, you need to be able to relate these spectra together in a quantitative way. And this is why we get into calibrating the spectra in absolute flux. That is to try and convert the flux axis to physical units. And we use ergs per square centimeters per second per angstrom, which seems to be the most widely used within the professional world. That's what you tend to see in professional papers used to calibrate spectra that have been calibrated in absolute flux. There's one way there are several ways you can do this, but one that's very convenient within our community is to use a V magnitude, which is measured concurrently with the spectrum. And that can be used to do the calibration. This works provided the spectrum covers a sufficient wavelength range to cover the whole V filter passband. But many of the spectrum we're working with, the vast majority, in fact, satisfy that, either their low resolution or their E-shell spectra. Now, not everybody is able in a position to take a V magnitude at the time they're taking their telescope, although some people have a piggyback scope on the top of the main telescope that will record that for them. Or what we can do is we can use the AAVSO spectroscopic database. We take magnitudes there, work out daily averages, and then interpolate between those to the dates on which our spectra were recorded. In this simple example of AG Draconis over the last 5 years, a light curve of it shows along the top the times at which the spectra have been recorded by contributors to the database. Underneath in blue are the daily average magnitudes from the AAVSO, V magnitudes, V band magnitudes, and in red are the spectra, the V magnitudes interpolated onto the particular days at which spectra were recorded. So that enables us to obtain V magnitudes for all our spectra, which we can use to calibrate the spectra. And with Python, it's relatively quick to apply that calibration for, say, all the spectra in a particular star. That can be done in a few minutes, but the results are then much more useful for subsequent analysis. Just a very quick explanation of how to do that. It's based on using standard spectra from, say, the HSD CalSpec library, which you can find on the internet. For these, each spectrum has an absolute flux calibration, but also a magnitude. And if you multiply a spectrum from the CalSpec library with the passband of a V filter, a typical V filter, you will find the amount of flux transmitted by that filter. And that allows you to develop the relationship between the V magnitude and absolute flux. You then take a relative flux spectrum of the star you're interested in. The example there is AG PEG. You have its magnitude, be 8.62. If you then multiply that spectrum by the V filter passband, you will get what the transmitted flux is in relative flux unit from your relative flux spectrum. But you also know from the relationship you've derived earlier what that magnitude corresponds to in absolute flux. The ratio between these two numbers, you can then use to multiply your relative flux spectrum and produce an absolute flux spectrum, as I show you at the bottom left, where the vertical axis now shows absolute flux. And that works remarkably well. There are other ways you can do it, but this we found to be very successful. And it certainly, you can check this with other, if you go and look at spectra, say from the new generation spectral library, NGSL, which are absolute flux calibrated, you can apply the technique there and you'll find that it gives you a pretty accurate flux calibration that matches the spectra in that library. So what you then want to do is well, we've now got a process of producing absolute flux spectra. How consistent is that from observer to observer using different equipment, different software? I just picked 3 spectra here from different observers that happened to be observed on the same night, 21st of April this year, of AG Draconis. They were recorded by these 3 people. V magnitudes were either measured by the observer or interpolated, as I described earlier. The observers corrected their spectra for atmospheric and instrumental losses, and then calibrated them in absolute flux, or I calibrated them when I read them down from the database. But what's interesting is when you plot them up together, they agree pretty well. And that gives some confidence. And you see this when you look at large batches of spectra from the database, that the absolute flux does agree very well and is a consistent way of calibrating the spectra. So once you've got your spectrum, the whole spectrum in absolute flux, you can start looking at the flux in individual emission lines. Now, if you take a spectrum like AG PEG, it's got a complex spectrum, and Francois will tell you a lot more about this in his talk following mine. But the contributions in this will come from an M3 giant star, when that produces a wind, and that wind envelops a hot white dwarf, which issues a lot of radiation, which produces emission lines in a surrounding nebula, composed of the wind from the giant star and possibly from the white dwarf. So a very complex system, which is why it acquired the name Symbiotic, because there are this symbiosis between very hot objects and very cool objects in the wind. Now, to measure the flux in, say, the H alpha emission line over towards the right-hand end of the spectrum, the base level of the continuum is produced by an M3 giant star. So if you subtract that spectrum, you will find the part of the spectrum which is due to the emission in H alpha. And just to highlight that, if I highlight the bottom of the line, you'll see the blue line is the spectrum, typical spectrum from a library of an M3 giant star. And above it is the emission line. It's the area of that emission line that we're really interested in. Now, what you can do in Python is you can normalize the two spectra together, the spectrum of AG-PEG, say, and the giant star spectrum on either side of the emission line. And then what you have to do is do a numerical integration of the region that's shaded yellow there between the giant star spectrum and the emission line itself. It's a relatively straightforward thing to do once you have the data in that form. You've got to take some care when you're doing that, because if you're running this through a lot of spectra, the algorithm has to take into account things like the variable resolution of spectra. Some lower resolution spectra are wider than others, so the width of the area that you're integrating over has to be correspondingly that little bit wider. Some stars have a significant radial velocity, which shifts the central peak of the emission lines by possibly up to several angstroms. So you have to, again, take that into account when you're defining the region that you're integrating over. And even if the wavelength calibration is inaccurate, which displaces the line, if you take note of where the peak of the line is, you can adjust the region that you're going to integrate over. So even spectra which have maybe slight problems with wavelength calibration can still yield perfectly useful values of line flux. You can also calculate the equivalent width of spectrum in angstroms by rectifying a spectrum. That's dividing the spectrum by the continuum under the line. However, you need to be aware there is something that can catch you out here, and this example shows this is a spectrum of, or a timeline, a light curve in the top of AX pair, a symbiotic star. It's actually the top spectrum is the continuum of the level of the continuum in the vicinity of the H alpha line. That very much mimics the actual light curve of the star itself. Under it is the equivalent width, which you calculate from that spectrum by rectifying it. But if you look at the lower spectrum, it actually shows you that the H alpha line flux has no peak in it. That is peak you would measure in equivalent width is spurious. It's simply caused by the variation in the continuum level under the line. So you do have to be careful. A lot of professional papers work with equivalent widths, and they have to be very careful when they do that. They're not seeing an effect which is actually caused by a variation in the continuum of the line. And that's one reason we like working with the absolute flux of the spectrum and correspondingly the flux of the line itself, because it gives you a clean picture of what's actually happening. Now, in anything that you measure, you have to also start to think about, well, what are the sources of uncertainty in making that measurement? And certainly in line flux, there are a variety of potential contributions. The simple statistic variation you get from from signal to noise in the spectrum, yeah, you can measure that and assess how large that uncertainty might be. If you're flux calibrating the spectrum from a V magnitude, there will be an uncertainty in the value of that V magnitude, which feeds through into the level of the continuum of the spectrum throughout the spectrum. And also, if you're modeling the spectrum in order to extract an emission line, depends on how well you're modeling the components of the spectrum. Very often, it's simply good enough to linearly interpolate under an emission line to do that. But you should check that carefully to see that there aren't some strong features in, say, the giant star spectrum under a line that maybe you should be taking into account. And lastly, this thing I've been mentioning several times, if the response correction is not well done, it will distort the shape of the continuum. What it tends to do is to tilt the continuum either up or down at one end or the other. and that will then affect the value you get for the flux measured in a particular line. There are ways to try and estimate that. One way is to see how consistent a spectrum is with others recorded around the same time. And that usually is pretty good at showing you up when a spectrum is significantly divergent from that. And you can flag that spectrum up and decide what you want to do with it if you're going to process it further. But that's probably one of the largest sources we have of uncertainty in the spectra we have. But what is noticeable, if looking back over the spectra in the database from early days, this was quite a common problem with spectra. It's very rarely a problem now, and I think that's simply because people have become more expert and careful and understanding the problems when it comes to processing spectra. If you analyze all these errors and try and estimate the uncertainty in measuring line flux that they cause, it is about 10% for strong lines and maybe 20% for the weaker lines. These are ballpark figures, and they're certainly lower limits. You can get worse or larger uncertainties in some cases, but that gives you an indication of what is achievable with measuring line flux in this way. And if you can broadly confirm that, if you measure spectra manually using programs like Plot Spectra from Leicester, you can get a manual measurement and compare that with the algorithmically derived flux. And there's pretty good consistency between doing that. One thing it's nice to be able to do is to assess the accuracy of measuring line flux. And that's quite hard, because if you want to compare it with published data, that tends to be in the past. So you need to find a fair way of doing that. This is something I did with one symbiotic star V1329 Sig, which has been in quiescence for a number of years. It shows orbital modulation. If you phase the light curve on the known orbital period of the star, and then look at the variation of each of these emission lines. The black squares are published in a professional publication that analyzed the star about 5 years ago. The red crosses are data more recently, which really show that the flux level that we're getting is pretty accurate. It matches pretty consistently in all these cases with what has been measured professionally. This is a star that is stable enough for that to be a valid check, I think. Okay, now some results on analyzing spectra in the database using Python. Some of the data, how we calculate and plot the quantities. And the spectra in these plots have been contributed by over 100 observers who are regularly submitting their spectra to the ARAS database. And I would really like to gratefully acknowledge their contributions. Without their hard work and care in preparing and submitting their spectra, we wouldn't be able to extract the sort of information that I'm going to show you. AG Draconis, a symbiotic binary, slightly unusual because it's a K-type spectral type giant star. Most symbiotics have an M-type giant, but the spectrum is a combination of the nebular emission lines from hydrogen, helium-1, helium-2, and in this case, a couple of Raman lines. These are lines produced initially by ultraviolet radiation from the white dwarf, scattering of neutral hydrogen in the wind. And they produce these lines, which are really diagnostic of a symbiotic variable. There are relatively few conditions in astrophysics where you have this combination of extreme energy and relatively thin and cold neutral hydrogen. So if you see that, it's an indication you're probably looking at a symbiotic binary. And what we do is, by measuring the flux, we can produce tables of measuring flux for these emission lines. Here's just a short section of a table we publish in the newsletter. And this data is available to anyone who might want it. For each spectrum, these are the lines which are bright enough to be measured in this sort of way. We also show you the magnitude which was used to flux calibrate the spectrum, and also a quality flag, which is a bit subjective, but it's really our assessment of how well measured that spectrum is. And you can also plot the same data. Here we show plots of the various emission lines over the last approximately 5-6 years for that star. And then now you start to see the sort of interesting science that might be showing itself in these spectra. You could see, for example, at the lower right, the Raman line at 6830. The third peak in from that is really very prominent and strong. Whereas if you look at to the left of that at the helium-2 line, that peak is very much weaker. And the other two spectra are all different as well. So it's very potentially useful to have this information extracted from the spectra. And the other thing I would draw to your attention is the color coding. What these plots do show is in blue spectra which were recorded typically with an ALPI around a resolution of 600. The green points are typically recorded with a laser spectrograph of around 1000 resolution, and the red points are almost all obtained with an E-shell spectrograph, much higher resolution, typically around 10,000. But they lie pretty much on top of each other. The data you get from that huge range of resolutions in the database are all contributing in a consistent way to a picture of the behavior of these stars, which really justifies why it's useful even at the lowest resolution of 600 in an ALPI to contribute spectra which can lead to useful science. And here's another example, AGPEG, symbiotic binary, which about 5 years ago, in 2015 to 2017, it produced a classical, what are called ZN type symbiotic outbursts. And you can see the light curve just below that shows two peaks, one in the middle of 2015, which then faded, and there was a second peak, and then it faded back again, and eventually it went into the regular sort of modular or orbital modulation you get when the stars are in quiescence. It's believed that this event was probably due to nuclear burning on the surface of the white dwarf, that level increasing possibly because of an increased accretion from the red giant's wind, which leads to an instability. But these are very active research topics in astrophysics these days. To the right are again plots of the line flux, and you can see in the top three that they show different images or pictures or representations of that behavior that you see in the light curve. The H alpha line barely reacted at all during the first peak in brightness of the star. The H beta one showed a small increase, and then the helium-3 line responded quite strongly. But also interesting, if you look at the lowest plot, this is a forbidden line of Fe7, highly ionized iron. And that is almost initially almost in antiphase to the visual light output. The little red peak there aligns almost perfectly with the dip between the two visual peaks. And then while the Balmer and helium line fade fairly quickly back to quiescence, the iron line goes on getting stronger and gradually fades back down to a lower level. So there's obviously some interesting things going on in that object following the outburst, which it didn't all die down as the light curve might lead you to think it did. And just looking at more closely at the orbital modulation, it's got a 818-day orbital period. These things are very widely separated objects, the giant and the white dwarf, as again Francois will explain in more detail. But what you see is this orbital hump, which peaks around the phase where the white dwarf is in front of the red giant star as we look at it. And the reason you get a hump, it's believed, is that the white dwarf is irradiating the red giant star, and one surface of it is therefore hotter and eliminates more radiation. So you see a peak or a hump at that sort of orbital phase. You get the same effect in the emission lines, in hydrogen beta and helium-2, for example. They show the same, although the data is more sparse, it definitely shows that same behavior. And on the right, I show you a plot of the line ratio of these two lines. It's actually inverted because the rate of change of one of the lines of the helium-2 lines is considerably greater than the H-beta line, and that just inverts the picture. But I include that one because it's often used as a proxy for the temperature of the ionizing source, somewhere in the region of 15,000 Kelvin, sorry, 150,000 Kelvin. But it's probably not in this case. It's probably that this is likely variation caused by different visibility of the places these lines are produced. But I really just include that to show that it's complex how you interpret the data from these. And another interesting question is, if you actually take all of these plots and you fit a parabolic curve to them, you'd think it would peak at 0.5, but it doesn't. It peaks at 0.45. Not at 0.5. I don't know why that is. I've not seen that mentioned anywhere. It could be that we've got the ephemeris wrong, but that's a 40-day difference. And the ephemeris was confirmed relatively recently, only about 3 years ago. So something interesting is going on. This might also be telling you something about the nature of the environment within that symbiotic. And this last example is a nova that went off recently in Cassiopeia, one of the relatively few nova we get in the northern hemisphere that's easily accessible to most of us. Had a very interesting light curve, which you could see at the top right there. Particularly note along the top, the marks that show you where spectra have been obtained. ARAS observers have been really following this extremely well, and we have spectra covering all phases of this peculiar ups and downs of the light curve. Just to show you the difference that you get in the spectrum, the two black arrows show you the times at which the spectra underneath were recorded. When it was faint, the spectrum is fairly horizontal. When it brightens up, you get a much stronger peak spectrum, more activity in the lines. You get P Cygni profiles, these dips to the blue side of a number of lines, definitely develop. And you can make this comparison because these are all calibrated to the same absolute flux scale. And down at the bottom, I show you the H alpha line flux. And what's interesting there is that the H alpha line appears to be totally disinterested in the sharp increase in brightness of the nova. And it's only once it's faded back after that first peak that the H alpha flux starts to pick off. And then goes up and down and follows its own course. And to the left is a composite plot, which you can produce with Python, which shows, it's a good way of comparing spectra and looking at the time evolution of spectra. Where it's sensible, we'll produce pictures like that for the newsletter. And just looking at these spectra there, you can see how the slope of the spectra goes up and down following the brightness variations of the star itself. And just to draw your attention to this little group of lines here, these are lines of singly ionized iron, which form what is referred to as multiplet 42. And if we look at that top right there, you can see a magnified version of that part of the spectrum. And these three lines, all of which have small P Cygni dips. And on the left are the measured flux since day 0, when the outburst was first detected, how the three lines vary, and they follow pretty much the same pattern as would be expected. But what's interesting, what you can do once you've measured the lines, is you can look at the correlation between the flux in different pairs of lines. And what you see there is if the two lines at 4923 and 5018, there's a pretty much a linear correlation between them. You could get the ratio from that. And I think that tells you something about the environment in which the lines are formed. That the slope of that line, as I understand it, will change depending on the temperature of the environment. So you've got a means to monitor various physical conditions once you've access to these spectral lines. Okay, so just to finish, here are a list of papers that have been published over the last 5 years, which have used spectra from the ARAS database. So we're already being successful in getting professional astronomers to pick these up and use them. We encourage people writing papers that use these spectra to give acknowledgement, certainly give acknowledgements to the observers. We really would like people to mention the individual observers' names in the acknowledgements. That's what we're asking them to do. And also, if a particular contribution from a particular observer or group of observers makes a really significant contribution to the scientific analysis, we suggest that that would be appropriate for these people to be invited to be co-authors of the paper. So we're trying to really give recognition as far as we can to the work that the amateurs are doing, because I believe that the work of amateurs is now making a very significant contribution to professional astronomy. And there are many ATALs produced that refer to the work of the ARAS team altogether. So in summary, really, the ARAS database and the newsletter are supporting and promoting small telescope spectroscopists. I think we're demonstrating that the scientific information obtained in these spectra is helping to encourage their use in professional publications. And we certainly feel that custom tools that we've developed have helped in achieving that. So thank you for listening. I'm happy to take any questions.
Thank you very much, David. That was a really good presentation, very interesting. I have a couple of questions.
Sure.
Just to start, what you did in analyzing this information in the ARAS database, is that something that anybody can do? You know, could I write a program and access the data and do the same sort of thing?
Absolutely. This is an open database. Anyone can take spectra from it and use them. There are no limitations other than that if you were to use them in a publication, we'd want acknowledgement of that. But the idea is that we want to see these as widely used as possible.
Okay, and the second question is the Python code that was used to do this analysis, is that available for people to look at or share anywhere, or do we each write our own?
I think it's an each write your own situation. I have written this to meet the objectives so that I had for trying to access this data. Like any code you write yourself, it's not designed for general public use. It would be a significant amount of work to turn a program like that into something you could generally release. I'd be very happy to work with anybody who's interested in doing more in this area, because it's been a steep learning curve. I've really taught myself Python over the last year and produced programs but to do this sort of thing. But Python is a very good environment for doing that. So there's a lot of stuff already there, utilities and functions that you can incorporate. It makes it an awful lot easier than if you were starting from scratch. So certainly I'm willing to help anybody who wants to go down this road. Okay, and then finally, what suggestions would you have for people starting out doing this, as far as, you know, do you have any recommendations for kind of how to get a head start from lessons that you've learned over the course of the last year? You know, like where would a person go to start? Well, most organizations run mentoring programs. I help mentors, people contributing to the BA database and to ARAS. But there are, particularly in the US, there's a very active scheme being run by Woody Sims that you know, who holds online discussion meetings which help people get up to speed and handhold people. I would suggest people might get in touch with Woody and discuss with them whether, if they're seriously wanting to be productive in producing spectra which can be submitted to a database, then we will try and help them do that and learn the ropes. It is a learning curve, but if you're motivated and you are keen to do this, there are people around who will help you do that. And the end result of producing a spectrum which you know contains useful science is, I think, a good incentive for people to want to do this.
Okay, I have two questions here to ask that were posted on the Q&A section of Zoom. The first one is, are there some public examples of Python to get started?
Yeah, there are lots and lots of them. I learned my Python with the aid of Google, and I would suggest anybody who wants to find out about Python, start exploring. There are a lot of online resources. There are documents you can download. It depends on how you like to learn a language. I tend to just pick it up by posing a task to Google and say, how do I do X in Python? And you will find somebody has posted an answer. And that way you gradually learn how to do it. There are many Python, astronomical Python packages around which are good to just look at and learn techniques for coding from. So there are many sources of information available. Most of them are online.
Okay, and Phil, who asked that question, had a follow-up saying that he wasn't specifically asking about Python in general, but referring to the Python that you used to access the database. Are there examples of how to go about accessing the database? Absolutely, yes. It's a good question. My answer really was in the spirit of astronomical software. Facilities like AstroPy and all of the associated packages that are around that are well documented and are discoverable on the internet. And I think that's what most professional applications are based on as well. So all of that information is available to anyone to use and to learn from. Okay, and then finally, Stephen wanted to know if Python is runtime or whether you need a compiler for it. It's runtime. It's a scripting language. Yeah, you just write the code and run it. So it's easy to debug and for that reason. You get instant feedback when you run it. It's not always the most clear error messages you get. You have to figure out why it's produced a strange message in some, because often that's buried down in some nested level of Python routines. But eventually, if you're persistent, you will track down the bugs and get them out of your code. All right. Well, thank you very much, David, for an excellent presentation. We appreciate it. Thank you. And next up, it's a logical transition here from your presentation to the next presentation, which is by Francois Teyssier. Francois is the creator of the ARAS database, but he's also an expert on symbiotic stars, which he's been studying, I think, since at least 2009, from what I could determine. He's also the author of the guide that I mentioned last week in my introduction to spectroscopy about doing low resolution spectroscopy and the low resolution observing guide, which I think is excellent. And if you're interested in low resolution spectroscopy, is a perfect thing for everybody to search for on the internet. And so with that, I'd like to turn it over to Francois. However, he's having some issues, or anticipated some issues in France with internet speed. And so Francois' presentation will actually be a recording. Although, as you can see on your screen, Francois is available and he's there, and we can ask him questions after the recording is over. So I believe that Lindsay will start that recording for us.
Yep, I'm getting there.
Hello, bonjour from France. The symbiotic stars form a small class of interacting binaries. Their spectra show variations related to the orbital phase and the activity of the system at various time scales, as the result of astrophysical phenomena such as winds, accretion, outbursts, and nova event. Despite the impressive amount of data collected so far, they are still not well understood and subject to many debates. For these reasons, ARAS group undertook since 2009 a spectroscopic monitoring and contribute to the knowledge and comprehension of these peculiar systems. During this talk, I will summarize the current knowledge about symbiotic stars. Then I'll show a few examples of their behavior illustrated with ARAS spectra and the usefulness of this data for scientific research. A few years after a publication about AQR, Paul Merrill acquired the very strange spectra of 3 stars showing helium-2 in emission. A recombination line which needs a ionization temperature of at least 50,000 degrees, and the continuum of a M-giant star whose temperature is only 3,000 degrees. The same Paul Merrill introduced the biological concept of symbiosis to define the new class of symbiotic stars using the Andromeda as prototype. The catalog produced by Basinski and al. In 2000 proposed the most recent spectroscopic definition. Kenyon, in his monography, pointed that symbiotic stars sometimes do not match with the classification. As an example, the well-known CH Cygni were considered as a standard in normal M-giants classification until the 60s. Thus, a more physical definition is emerging. Any binary where a white dwarf accretes enough material from a red giant, such that interaction can be detected at some wavelengths, is called a symbiotic star. The interaction between the 2 stellar components of the binary forms the 3 ingredients of a symbiotic star. The red giant as the donor star, whose wind is accreted at the surface of the white dwarf, which ionizes the nebula. All symbiotic stars are variable. Most of them show high states during which multiple outbursts can occur with an amplitude ranging from a few tenths to about 3 magnitudes in the visible range. During low states, only orbital variations are observed. The AAVSO light curve of Z and collected since 19,000 illustrates perfectly this behavior. We can note the great variability of the outburst profiles, both in amplitude and duration. Now, let's go in more detail about the symbiotic system. The red giant, the hydrogen is burnt in an envelope around the core of helium. The radiation pressure dilates the envelope to giant dimensions, with the consequence of a very high luminosity, despite the low temperature of the external layers. Typical luminosity is several thousand times the luminosity of the sun. As a result of the extended atmosphere of the star, the gravity is very low in the photosphere, leading to a high mass loss in the form of a strong stellar wind, whose typical value is over 10 to the power -8 in units of solar mass per year. The graphic on the right shows the mass flows according to the spectral type of the white giant. The order of magnitude of the velocity in the wind, increasing with the distance from the star, is of tens of kilometers per second. Various studies establish that the mean spectral type in symbiotic systems is M5, later than those observed in single white giants. Moreover, different studies establish the typical order of magnitude of the mass flows from the white giant in symbiotic systems. 10 factor minus 7 in units of solar mass per year. High mass loss is a key point for understanding the symbiotic phenomenon. However, some giants in symbiotics belong to the K or even G class, producing the subgroup of yellow symbiotics, such as G draconis. As a result of its low temperature, the spectrum of white giants peaks in the high air. The shape of the continuum is deeply affected by the absorptions produced by the TiO molecules. Several indexes measuring the depth of the TiO bands allow to determine the spectral type of the white giant. In symbiotic stars, this measure is significantly affected by several radiative processes. It doesn't allow the determination of the true type of the white giant. However, it can be used as a powerful diagnostic tool to trace the activity of the system. As an example is shown, the variation of the TiO1 index of CI Cygni during an outburst in 29 monitored with a LiWES 3 at low resolution. Due to its high gravity, the white dwarf accretes material from the white giant wind. This material forms an hydrogen-rich envelope at the surface of the core of the white dwarf. From the luminosities of the hot component, it appears that symbiotics can be divided in two classes. The hot component of the low luminosity symbiotics, such as HEN, have a luminosity 10 times the solar luminosity as an order of magnitude. Slow luminosity can be produced by the energy released by the accretion at the surface of the white dwarf. They are called accretion-powered symbiotics. The luminosities of the second group, from hundreds to thousands of solar luminosity, cannot be produced by accretion only. They are produced essentially by hydrogen nuclear burning in the accreted envelope, as the energy released by proton-proton fusion is 60 times higher than the accretion energy on a 0.5 solar mass white dwarf. The regime of accretion on a white dwarf of a given mass depends on the weight of accretion. The accretion weight is low under the curve m dot critical. The accreted matter is degenerated and does not react as a perfect gas. In this case, the temperature increases until the Fermi temperature, producing a nova event with the expulsion of a part of the envelope as an ejecta. This is the case for classical novae. In a few cases, the symbiotic stars can produce very slow nova events, such as EG-PEG, the slowest nova even recorded. But this is not the case for most of symbiotics, as the accretion weight is greater than the critical weight. The matter of the envelope responds as a perfect gas and thus expands to large dimensions. Thus, study burning hydrogen. It produces a large and hot envelope, which explains the high luminosity of the hot component in classical symbiotics. If the accretion rate increases above the curve mass loss table, for any reason, the envelope becomes unstable, inflates to the dimension of a giant star, and cools. The peak of energy shifts toward longer wavelengths. The degree of ionization decreases. This is a classical symbiotic outburst. Even if the mass loss from red giants is enhanced in symbiotic systems, the classical bonded oil accretion is too low to produce a sufficient accretion rate for a steady burning state. The red giant wind must be focused toward the white dwarf via an overflow through the Roche lobe or compressed toward the orbital plane as the result of the rotation of the red giant. Simple static models of ionization show that the nebula can be partially ionized, idest matter bonded, or largely ionized, idest radiation bonded, depending notably on the luminosity of the hot component. More sophisticated models, including the hydrodynamics of the system, are developed for a more accurate and realistic understanding of the complexity of the symbiotics. We can now summarize the model of a symbiotic star with the order of magnitude of the different parameters. In quiescent state, the hot component releases energy at almost constant rate. A key point is the high density of the nebula in comparison, for instance, to planetary nebula. In high state, produced by an enhancement of accretion and nuclear burning, the envelope of the white dwarf expands to giant dimension and cools. The wind from the hot component increases in both mass and velocity. Ionization and recombination regimes change. The slide summarizes the formation of the spectrum. The red giant contributes to most of the spectrum in the visible range. The hot component emits radiations in the UV and far UV. For those radiations, the nebula is optically thick, which produces ionization. Thermalization and recombination of the free electrons produce a nebular continuum. The tail of the light emitted by the hot component can be observed in the blue range of the visual spectrum. These three components forms a composite continuum. The desexcitation of the recombined electrons produce emission lines of hydrogen, helium, oxygen, and other metals such as iron. Free electrons can exceed the various ions, producing the so-called forbidden lines in the parts of the nebula where the density is sufficiently low. As an example, the continuum of the spectrum of Teyssier differs significantly from the reference in the blue part of the spectrum and for the various TiO bands in the red range of the spectrum. The continuum of Teyssier can be modelized by the addition of a M5 spectrum, the black body spectrum of a white dwarf, and the nebular continuum. For this graph, the coefficients A, B, C were computed with a simple Excel solver. The values used for the modelization bring information about the physics of the object. We shall now illustrate the complex behavior of symbiotic stars, beginning by symbiotics at quiescence. The end is an accretion-powered symbiotic with a low luminosity hot component. Only a few and often weak emission lines appear in the spectrum. Balmer lines, Fe1 triplet 5866, and O3 on the continuum of M2 white giant. It is one of the brightest symbiotics with a mean V magnitude of 7.2. It has never been observed in outburst. According to the orbital phase, the light curve shows a double wave variation which can result from the illumination of the white giant by the hot component, an ellipsoidal effect produced by the shape of the white giant filling its roche lobe, or colliding wings. The intensities and profiles of the lines vary significantly from absorption to emission. An example is shown with the H-alpha profile at various orbital phases. Basically, the variations of the profile can be explained by the variation of the optical depths according to the orbital phase. The optical depths being, of course, higher at phase 0.5. But the differences between profiles at phase 0.25 and 0.75 evokes a more complex reality. Using essentially ARAS spectra, Natalia Shagatova, Augustin Skopal et al. Studied the orbital variation of H-alpha line using a Gaussian fitting of the line with 3 components. The observed profiles can be described by the sum of a broad emission component and 2 intense emission and absorption. The absorption being slightly shifted toward the blue. The orbital variations of the emission and absorption components allow to constrain the models for the star, concluding notably to the asymmetry of the nebula. More detailed publication, including O3 line, is currently under review. The I Cygni is a classical symbiotic star, most often in quiescent state. It is a nuclear burning symbiotic. The luminosity of the hot component is about 500 solar luminosity, and its temperature about 120 kilokelvins. With H-L spectra obtained during an orbital cycle from 2015 to 2017, comparison of the absorption lines of the continuum with the spectrum of a single M-giant star. Using a cross-correlation method, we compute the radial velocity of the white giant with an error of about 2 kilometers per second. These velocities are shown with respect to the orbital phase. Using the software SBS, we computed the orbital elements. See the white column of the table, which are in good agreement with previous published studies. We added a study of the center of various ionized lines. The radial velocity of He2 line is clearly in antiphase. We can conclude that the zone of formation of He2 is strongly linked to the motion of the hot component. Balmer lines in symbiotic stars show typically an asymmetric profile with an absorption blue shift according to the radial velocity of the system. Moreover, broad wings appear in the pedestal of the profile. The blue shift absorption can be produced by self-absorption. The origin of the broad wings is subject to debates. It may be formed in the wind emitted by the hot star, by scattering, or in the region of the ionization front. The profiles of selected lines show that they are formed in various regions of the nebula under different physical conditions, such as the density, electronic temperature, or velocity gradients. The time series of various lines during the orbital cycle are used to build models of the system. We note the smooth variation of Fe7. On the contrary, the variation of O3 is much more complex, with notably a significant difference between the beginning and the end of the orbital cycle. I call your attention to the complex evolution of H-beta line in only 3 months during the egress of the eclipse of the hot component by the red giant. To date, there is no model explaining this behavior. The I cannot see monitoring of symbiotic stars serve often more to illustrate the complexity of the systems than to clarify or understanding, said Gagnon in his monography. AX pair is another classical symbiotic with a luminous I component. On the M5 continuum, we observe the emissions of hydrogen, helium-1 and 2, oxygen 3, I1 ionized 6 times. The long-term line curve shows the alternance of high and low states. During high states, outbursts can occur with very variable shapes. During low states, a wave-like profile appears, very variable from one cycle to another. The duration and profile of the eclipse is strongly variable. Since 27, an outburst behavior appears at about orbital phase 0.5. In 2019, as shown by the brown curve, an outburst occurred just at the end of the eclipse. This flux calibrated spectra acquired by David Boyd illustrate the behavior of AX pair during the outburst. The outburst is detected at the end of the eclipse of the hot component. During the rise of the outburst, the blue and green spectra, the intensities of most of the emission lines increase as the result of the enhancement of the ionization and recombination processes. Low excitation complex C3N3 appear. The ionized line of Fe ionized 6 times vanish. During the decline of the outburst, the continuum of the red giant is deeply affected by the nebular continuum, while the intensities of the emission lines decrease steadily. Green and red spectra in the bottom graph. Note also the enhancement of a strong blue continuum as the result of the shift of the luminosity peak of the hot component toward the visible range. The high tendency of the monitoring allows to date precisely the evolution of the spectrum. During the rise of the outburst, the high ionized lines of Fe7 switch off very early. A few days after, the TIO index decreases steeply. The other lines increase until the maximum. He2 intensity drops suddenly just before the maximum. The ratio He2 H-beta can be used to approximate the temperature of the hot component. We note a smooth decline of the temperature during the rise and a sharp decline at the maximum of the outburst in visible range. Another example with an outburst of the prototype Z end in 2018. The spectra obtained during the outburst were studied by Jaroslav Merk and al. One important result is the profile of H-alpha line. During previous outbursts, which occurred since 2000, satellite components appeared in the blue and red sides of H-alpha line. They are attributed to a jet formed as the result of the apparition of a disk around the white dwarf. During the outburst observed in 2018, nothing of jets was observed. We conclude that each outburst is different and must be studied to constrain the models. During the introduction, I pointed only an expansion of the envelope of the white dwarf as an explanation of outbursts. In reality, the situation is much more complex and still not well understood. We hope that our high cadency monitoring will help to understand the nature of outbursts through their diversity from an object to another, and even for the same object. We conclude that the highest cadency of monitoring is required during the outbursts of symbiotic stars. The last example, H.G. Draconis belongs to the small subgroup of yellow symbiotic stars. The KT giant is of low metallicity. For that reason, ion lines are absent. In contrast, the spectrum shows strong Raman bands at wavelengths 6830 and 7065. These lines were identified in 1980 as the result of the scattering of O6 lines emitted in the far UV by the Lyman beta photons. These lines are observed in about 50% of the symbiotic stars. This is the only chance for amateurs to observe the far UV. The light curve of H.G. Draconis show an alternance of quiescent and active phases, which can result of the combination of the orbital period about 550 days and the pulsation of the giant about 330 days. From the different evolution of the Raman O6 lines during the outbursts, these outbursts have been classified as hot outburst if the Raman O6 remain in the spectrum, or cool outburst if it disappears. On the request of Rudolf Gallis and his colleagues, we pursue since 2015 a monitoring of H.G. Dra and observed 4 outbursts. The analysis of essentially ARAS spectra acquired at high cadency shows that the evolution of the outbursts, at least those observed during our monitoring, is more complex than provided by the classification hot-cool outbursts. Within the same outburst, periods of cooling and warming can occur. This has led Rudolf Gallis and his colleagues to raise the question of a new type of outburst or a transition or a combination of hot and cool outbursts. At the date, our observations often lead to asking new questions rather than answering to old ones. Symbiotic stars as novae. The white dwarf of Teyssier has a rather low luminosity. Its mass is near the Chandrasekhar limit, thus it is a promising candidate for a supernova event, if the white dwarf grows in mass. As two nova events were recorded in the past, Teyssier belongs to the small group of recurrent novae. From a comparison of the B-band light curve of the 1946 event and the current one, here AAVSO data in blue dots, Schiffer predicts the next nova event in the middle of 2023. In 2015, a fast increase of the luminosity, notably in the P-band, were detected. This brightness was accompanied by significant changes in the spectrum. The series of low-resolution spectra illustrates the significant changes of the spectrum during the rise. The blue graph shows the spectrum at the end of the low state. Only Balmer lines are weakly visible. In the green spectrum obtained in 2015, Balmer lines increase and Fe1 lines appear. Fe2 is still very faint. Then, in the spectrum obtained in 2016, the intensities of all the lines increase. We note the high intensity of helium-2, the development of O3, and of the complex N3C3. These spectra were used by Christian Ilkiewicz et al. For a study of the beginning of the active phase. This is an answer to an often raised question: are low-resolution spectra useful? The answer is clearly yes. We continue the observations and the analysis of the data. We show a global decline of most of the lines, but an increase of the forbidden lines or 3. I come back on Schiffer predictions and show the current AAVSO light curve in B-band. In the data produced by Schiffer, it appears just before the nova event, a decrease of the luminosity. During our spectroscopic monitoring, we shall have to check this decline and increase the cadency of our observations. Firstly, to observe in detail the changes of the spectrum during this peculiar event, and secondly, to catch the chance of acquiring spectra since the very beginning of the nova outburst and during the very short rise. I can do it. I call your attention on ARAS of another symbiotic recurrent nova, whose nova outburst is predicted for the next years. We monitor the star upon the request of Natalia Shagatova and Augustin Skopal. On the request of professional teams, we participate to the discovery and classification of symbiotic stars. A new symbiotic star were identified from a spectrum acquired by Terry Bolsen. Another positive result is under publication. The reactivity of the team allows the identification of new stars during outbursts, such as V426 SGE in 2018, with a spectrum obtained by Paolo Berardi. point just introduce the data. Thus, I will only present the current improvements. With the support of a PhD student, an automated database is under construction. It should be available in a few months. The database is the result of the involvement of more than 80 observers since 29. Many thanks to all of them. As said by David, we produce a quarterly newsletter which is indexed in the EDS system. I will conclude on the kind comments from some of the professional teams we are working with. Waiting for new spectra, I thank you for your attention. All the best.
Thank you very much, Francois, for a very good presentation. That was extremely interesting. We do have a couple of questions here. I think you might have seen the first one. Can symbiotic star outbursts be predicted, and where would that data be found?
Not precisely. The same as for dwarf novae. SS Cygni, dwarf nova, shows outburst from about 20 days to 80 days, but we cannot predict exactly at what moment it will produce a dwarf nova event. The same, of course, for symbiotics. There is some regularity for some of them. An example is produced by LG Draconis, but it can be the result of the bit period from the pulsation of the giant and the orbital period. But generally speaking, there are not so much outbursts detected since, say, 1 century to have really good precision of the next outburst. Perhaps we shall have as a nova outburst the prediction produced by Brad Schiffer. We'll see. So we have to take the more spectra as possible.
Okay. Thank you. James Lee wanted to know, can you explain the mechanism for how the nebular continuum is produced and the difference in location of the nebular continuum and the nebular emission?
Nebular continuum, not so easy. I would suggest you see it? Sorry.
It's hard to read. Can you hold it?
Osterbrock, yeah. This is very well explained in this book. In fact, this is the result of the loss of energy of the electrons when they recombine to anion. This excess of energy, of kinetic energy, produces a photon. And the sum of the photons produced during the recombination to any level of the ion will form a continuum spectrum, invisible range. It is called also Balmer spectrum for hydrogen, but not also that helium recombination produce also recombination nebular spectrum. Is it clear now?
Yes, thank you. And can you read the title of that book?
Ah, yes. This is Astrophysics of Gaseous Nebulae and Active Galactic Nuclei by Osterbrock and Fairland.
Okay,
So
and I think that Woody
really
has
a reference book produced by University Science Books, and my reference is 26.
Okay, thank you very much. And Woody listed the name of the book in the chat section as well with the authors, so that is very helpful. Thank you, Woody. I have a question for you. If a person was interested in submitting spectra of symbiotic stars to the ARAS database, how do you go about getting started?
Can you repeat just the end of your question?
Yeah, how does a person get started submitting spectra of symbiotic stars to the ARAS database?
They have just to send a message with the fit spectrum to my email address and a copy to ARAS eruptive star database for double check by David Boyd and Woody Sims, because it is very important for us to check the identity of the object, but also the calibration and the response curve in order to get the better level as possible for the database, in order that professional teams are confident using our spectra.
Of course. Okay, thank you very much. Well, it was a great presentation. I think it was a great day today. Excuse me. I really appreciate the hard work that all the speakers put into this today and the great presentations we had. Tomorrow, we'll be back with a set of presentations focused primarily on hardware. And we will talk about the UVEX, Star Analyzer, LIRES 3, the ALPI, the LISA, the Eshel, DIY spectrographs by Tony Rhoda. And we have a presentation at the end of the day by Woody Sims on how to organize your observing sessions, which I think is a super good topic and will be an excellent presentation. So we'll look forward to seeing everybody back here tomorrow at 1600 UTC. And then before we leave, I think Lindsay has something that she'd like to add.
Hi, thanks to you all for being here today. I do just want to add that in your email this evening, you'll get an email from me, and in that email will be 6 different links, because Ken's workshop is breaking out into simultaneous breakout sessions tomorrow, and each of those sessions has to have a different URL, and so those will all be coming to you in your email today, and that way you can easily hop between sessions tomorrow.
Thank you, Lindsay. And
passwords for those links.
Yeah, just so that everybody knows, this is a tremendous amount of work that Lindsay has done to get all of this organized so that we can do these breakout sessions. And it's not simple and it's not straightforward. And so thank you very much, Lindsay, for doing that for all of us. We appreciate it.
Oh, of course, I'm so happy to, and I'm so happy you've put together this program, and I'm really happy that everyone is having such a good time in this program and is getting so much out of the education.
So everybody have a good evening. Enjoy your Friday night or Saturday morning, whatever it is, depending on where you are in the world. And we'll see you again tomorrow at 1600 UTC.